a quiet corner of the internet where curiosity and calm live side by side. If you're settling in for the night, make yourself comfortable. Let the noise of the day fade away and allow your thoughts to drift through the quiet rhythm of science told slowly. Tonight, we're exploring one of the universe's most mysterious and beautiful ideas: quantum energy. It's the energy that hums beneath everything, from the faint glow of a star to the still air between atoms. You can't see it, you can't hold it, and yet it moves the cosmos. Before we begin, I'd love to know, where in the world are you listening from tonight? Whether you're under a blanket, lying in the dark, or gazing up at a ceiling that feels a little like a night sky, you're part of a quiet community of curious minds all winding down together. If you enjoy these quiet, late-night explorations, a gentle tap on the like button and a quick subscribe would mean a lot. It helps more curious minds find their way here. To those who are already part of this sleepy little community, thank you so much for your continued support, and if you'd like to join us on future journeys, be sure to click the notification bell so you won't miss the next upload. Oh, and while you're here, feel free to wander over to my new channel, The Sleepy Astronomer, where we drift even further into the stars. Now close your eyes if you like, breathe deeply, and let's begin our quiet descent into the smallest energy of all. What if even the emptiest space is never truly empty? Energy. We talk about it every day, yet few of us stop to ask what it truly is. It heats our homes, drives our machines, and glows within every star. But when we peer deep enough, beneath matter, beneath atoms, energy begins to blur into something stranger, something quantized. The word quantum simply means a discrete amount, a tiny packet of something that can't be divided further. At the dawn of the 20th century, scientists discovered that energy doesn't flow smoothly like water. It arrives in steps, tiny bursts, each one an indivisible spark of reality. This was the beginning of quantum physics, the study of a world so small that the rules of logic start to bend. In this hidden realm, light behaves as both wave and particle. Matter dissolves into vibrations, and what we call nothing, the empty space between things, turns out to be alive with invisible motion. It's a universe that never rests, a restless ocean of fields and fluctuations that form everything we see. Over the course of this journey, we'll wander from the first moments of quantum discovery to the vast silence of space itself. We'll meet the scientists who uncovered the strange and sometimes reluctant truths of energy. We'll trace the story of how the smallest quanta of light give birth to matter, to stars, and ultimately to us. But most of all, we'll learn that energy isn't a thing to be found. It's a rhythm that all of existence dances to. It is change itself written into the fabric of the cosmos. So as you lie there, letting your thoughts float like dust in a beam of light, consider this. If everything in the universe is made from energy, and even emptiness hums with it, then where does energy itself come from? At the end of the 19th century, science felt almost complete. The great physicists of the day spoke of their discipline as though it were a grand house already built, with only a few small cracks left to plaster over. Gravity, motion, electricity, all were neatly described by the mathematics of Newton and Maxwell. The world seemed to follow elegant, predictable rules, yet, hidden in the glow of something as ordinary as a hot piece of metal, there was a mystery that refused to behave. When scientists heated objects and measured the light they gave off, the results made no sense. They called these glowing objects black bodies, not because they were dark, but because they absorbed all light that fell upon them. When heated, they shone in beautiful gradients of colour, dull red, orange, yellow, white. But when physicists tried to calculate exactly how much energy these objects emitted at different wavelengths, the numbers exploded into nonsense. Classical theory predicted that as the wavelength of light grew shorter, as it reached toward the ultraviolet part of the spectrum, the amount of radiation should increase without limit. If that were true, even a small warm object should shine with infinite energy, a catastrophe in every sense of the word. This absurd result became known, somewhat dramatically, as the ultraviolet catastrophe. Enter Max Planck, a quiet, precise German physicist with a fondness for order. He was not the type to chase cosmic mysteries. He preferred neat mathematics and tidy answers. In the year 1900, Planck was trying to make sense of this black body puzzle. Perhaps, he thought, there was some small correction to the formulas, some missing factor that could smooth out the chaos. But when he adjusted his equations, no gentle fix appeared. To make the numbers fit the experimental data, he was forced to make a bold and strange assumption. The energy of light was not continuous. It came in discrete chunks. This was a shocking idea. For centuries, scientists had imagined energy as a smooth wave, something that could be divided and subdivided forever. But Planck proposed that energy could only be emitted or absorbed in specific fixed amounts. He called each chunk a quantum, from the Latin word meaning how much. The size of each quantum depended on the frequency of the light. The higher the frequency, the larger the packet of energy. Planck expressed this relationship with the small constant, now known as Planck's constant, a number so tiny it defines the scale of the subatomic world. You could think of it as the universe's smallest coin, the minimum currency of energy exchange. For a scientist devoted to classical order, this solution must have felt like a confession. He later admitted that he had made the leap out of pure desperation, never imagining it would lead to a new physics. Planck was trying to save the existing world of equations, not replace it. But the universe had other plans. When he compared his new formula to experimental results, it fit perfectly. Every curve of the black body spectrum aligned like notes in harmony. In that quiet triumph, Planck had unknowingly struck the first chord of a new era. What made this so profound was not just the correction of a mathematical error, but what it implied about reality itself. If energy could only come in fixed packets, then nature was not smooth and continuous after all. Beneath the flow of light and heat lay a hidden granularity, a digital texture to existence. It was as if the universe ran not on analog waves, but on cosmic code. Of course, Planck did not see himself as a revolutionary. In lectures, he presented his findings modestly, as if embarrassed by their strangeness. Yet, within a few short years, younger scientists would seize upon his idea and carry it far beyond what he ever intended. His reluctant hypothesis would ignite the most profound transformation in physics since Newton, a transformation that would change how we view light, matter, and even the concept of reality itself. Planck's discovery was also a reminder of how science often advances, not through certainty, but through discomfort. He wanted tidy numbers, not a revolution, but the data refused to yield until he surrendered to something radical. Sometimes the smallest step taken reluctantly can open a door no one expected to find. To imagine the scale of what he uncovered, picture this. If you took all the energy emitted by a warm object and divided it into the tiniest possible pieces, each one would carry an amount proportional to Planck's constant multiplied by the light's frequency. For red light, the quantum would be small, for blue, larger. These packets are unimaginably tiny, yet every beam of light that has ever shone, from candle flame to galaxy, is made of them. The idea that energy came in quanta was so alien that many scientists resisted it for years, but quietly it worked. Every experiment agreed. Slowly, grudgingly, the physics community began to accept that Planck's strange little constant was real, and that the universe beneath its smooth appearance ticked to an invisible rhythm. There is something almost poetic about it. The smallest possible action, the faintest whisper of energy, defining everything that happens in the cosmos. A single number linking the warmth of a hearth to the glow of the stars. Max Planck once said that new ideas in science don't triumph because old scientists suddenly agree with them, but because new scientists grow up familiar with them. He was right. His reluctant leap reshaped the world, whether he wanted it to or not. From that first spark, that desperate attempt to fix an equation, the quantum age began, and with it, a deeper understanding of energy, not as a smooth wave of motion, but as the universe's smallest, most perfect heartbeat. A few years after Max Planck's reluctant discovery, a young patent clerk in Switzerland was quietly thinking about light. His name was Albert Einstein. At the time, he was 26 years old, working long hours examining inventions for the patent office in Bern, and spending his evenings wrestling with the riddles of physics that no one else seemed to notice. In the year 1905, a year now remembered as his Annus Mirabilis, or Miracle Year, he published a series of papers that would forever change how we see the universe. One of those papers tackled a puzzle so ordinary it almost seemed unworthy of his genius. Why does shining light on certain metals cause them to release tiny sparks of electricity? This was known as the photoelectric effect. Physicists had already observed that when ultraviolet light was directed at a metal surface, electrons were ejected, creating a measurable electric current. But the details were strange. Brighter light didn't necessarily knock out more energetic electrons. Instead, only light above a certain colour, or more precisely above a certain frequency, could dislodge them at all. No matter how intense a beam of red light was, it simply did nothing. Yet a faint beam of blue light could cause an instant spark. Classical physics couldn't explain it. According to the wave theory of light, increasing brightness should increase the energy of the electrons. It didn't. Einstein, reading Planck's work carefully, took a daring step. What if Planck's strange idea that energy came in discrete packets applied not just to how matter emitted light, but to light itself? What if light wasn't just a smooth wave, but a collection of energy quanta, tiny, indivisible particles of pure energy? He called these particles light quanta. Today, we know them as photons. Each photon, Einstein proposed, carried an amount of energy proportional to its frequency. The higher the frequency, the higher the energy. Blue and ultraviolet light have shorter wavelengths, meaning more energy per photon. Red light has longer wavelengths and less energetic photons. When a photon strikes the surface of a metal, it can knock out an electron only if it carries enough energy to overcome the electron's binding energy. A bright red light may throw countless photons at the surface, but if each one lacks the required punch, none will succeed. A single ultraviolet photon, however, can do the job instantly. This idea was revolutionary because it shattered the comfortable certainty that light was a wave. For centuries, experiments had confirmed light's wave-like behaviour. It could bend, interfere, and diffract. But Einstein's paper said something radical. Light was both wave and particle. Depending on how you look at it, Light can ripple like water or strike like a hail of invisible bullets. It was a bold proposal, and not everyone welcomed it. Even Planck himself hesitated to accept the idea, yet experiments kept confirming Einstein's prediction. The energy of the ejected electrons depended solely on the frequency of the light, exactly as his equations described. The photoelectric effect was not only real, it became one of the most precisely verified phenomena in modern physics. Decades later, this discovery would earn Einstein the Nobel Prize, not for relativity as many assume, but for his explanation of light quanta. In everyday life, this strange behavior is all around us. Every time sunlight hits a solar panel, photons are absorbed by atoms in the panel's surface. Their energy knocks electrons loose, creating an electrical current. The same principle Einstein described in 1905. The light shining on your phone's camera sensor, the glow of an LED light, even the operation of automatic doors that use photosensors, all rely on the photoelectric effect. The universe, it seems, is built on this quiet transaction. Photons trading energy with matter, coin by coin. Each photon is a tiny packet of currency, a coin of light minted in the furnace of the universe, exchanged across the vast marketplace of reality. Some are forged in the heart of stars, some in your living room lamp, but all obey the same rule. No photon can give more or less energy than its frequency allows. This discreteness was more than a clever fix for an experimental problem. It was a profound shift in how scientists understood the world. Classical physics imagined energy as something smooth and continuous, like a flowing river. Einstein showed it could also behave like a shower of pebbles, and yet light never stopped being a wave. It was somehow both. This paradox would haunt and inspire physicists for the rest of the century. How can something be two things at once? How can a single beam of light travel like a wave but hit like a particle? Einstein didn't pretend to solve that puzzle. He merely pointed out that the evidence demanded it. The universe, he suggested, doesn't owe us simplicity. It only asks us to pay attention. There's something almost poetic in the idea. Imagine a beam of sunlight streaming through a window. To your eyes, it's a single, continuous ray. But in truth, it's an orchestra of photons, each one vibrating at its own frequency, each carrying a precise quanta of energy across the emptiness of space. They travel together for millions of years, only to end their journey by striking your skin, warming it by the smallest imaginable degree. That warmth, the comforting touch of sunlight, is the sum of countless tiny collisions, each photon giving up its energy to your atoms. Einstein's light quanta forced science to accept that nature is more mysterious than intuition suggests. It blurred the boundaries between energy and matter, between waves and particles, between the seen and the unseen. And perhaps most intriguingly, it hinted that the universe might be built from information, discrete packets of energy behaving like notes in a cosmic symphony. When you think about it, every light you've ever seen, every candle flame, every distant star, is telling the same story. It's a stream of photons, messengers from somewhere else, each one carrying its precise quantum of energy, unbroken, unchanged since the moment it was born. And so, from a small mystery involving a bit of metal as a beam of light, Einstein made the invisible tangible. He turned Planck's abstract quanta into something that could be measured, tested, and felt. He showed that light itself is both wave and particle, both continuous and discrete, both elegant and strange. A century later, the photoelectric effect still powers much of our modern world. Yet it also reminds us that even the most familiar things, like the light pouring through your window, are woven from mysteries deeper than imagination. Light, after all, is not just illumination. It is the universe communicating through energy, one photon at a time. After Einstein showed that light itself comes in tiny packets of energy, the next question was what this meant for matter. If light was quantized, could atoms be too? In the early years of the 20th century, atoms were still mysterious, tiny, invisible structures that seemed to defy explanation. Scientists knew they contained electrons and a positive nucleus, but no one understood why atoms gave off light in such precise colours, or why those electrons didn't simply spiral into the centre like miniature planets falling into a sun. It was a Danish physicist named Niels Bohr who found a clue, and he did it by listening carefully to the music of the atom. Bohr was young, brilliant, and endlessly curious. In 1913, while working in England, he began to reimagine the structure of the atom using the new quantum ideas that Planck and Einstein had revealed. He proposed something radical, that electrons could only occupy specific orbits around the nucleus, each corresponding to a distinct energy level. They couldn't exist in between these levels, any more than you could stand halfway up a staircase without a step beneath you. In Bohr's picture, an electron moving in its allowed orbit was perfectly stable. It would not lose energy or crash into the nucleus. Only when it jumped from one orbit to another did it emit or absorb a photon, a packet of light energy equal to the difference between the two levels. The greater the gap, the higher the frequency of the photon. This simple idea explained at last why atoms emitted light in such sharply defined colours. If you pass the light from a glowing gas through a prism, it doesn't form a continuous rainbow but rather a set of thin, bright lines, a barcode of colour. Each element has its own unique pattern. Hydrogen, for example, produces distinct red, blue-green and violet lines. These lines puzzled scientists for decades, but Bohr's model suddenly made sense of them. Each line represented a specific energy jump made by an electron within the atom. Every atom had its own internal ladder of energy levels, and those ladders were different for every element. It was as though every atom played its own tune in a universal orchestra, each note produced by an electron's leap between levels. Every atom hums a melody. Light is its song. The bright streaks of colour you see from burning elements are that atomic music made visible. Bohr's model was simple yet powerful. It worked perfectly for hydrogen, the simplest atom of all. Later refinements by other scientists would show that the story was more complicated for heavier atoms, but the principle remained. Energy levels were quantized, and electrons could only occupy those discrete spaces. Nature, it seemed, preferred order to chaos. This quantization also explained why matter is stable. In classical physics, an orbiting electron should lose energy continuously and spiral inward, collapsing the atom in a fraction of a second. But in Bohr's model, that was impossible. The lowest orbit was the electron's ground state. It could not fall any lower without violating the rules of quantization. In effect, the universe had built safety rails into the atom itself. Bohr's idea might sound abstract, but its fingerprints are everywhere. The very colours we see in the world, the red of a sunset, the blue of the sky, the green of a leaf, all depend on which photons are absorbed or emitted by atoms and molecules. When an atom absorbs a photon, one of its electrons jumps up to a higher energy level. When it releases a photon, the electron falls back down, releasing light of a specific wavelength. You see this most clearly in the glow of a neon sign. When electricity passes through the gas inside the tube, it energizes the neon atoms, exciting their electrons to higher orbits. As those electrons return to their original states, they emit light of a particular reddish-orange color. Change the gas, argon, helium, krypton, and you get new colors, each the signature of that element's quantum structure. Every glowing sign is a public display of atomic precision, a quiet concert of electrons jumping between notes. The same principle explains the colors of stars. When astronomers look at the light from a distant sun and pass it through a spectroscope, they see lines missing from the spectrum, dark bands where certain wavelengths have been absorbed by elements in the star's atmosphere. These missing lines act like fingerprints, allowing scientists to determine what the star is made of without ever visiting it. We can identify hydrogen, helium, sodium, iron, and even trace amounts of rare elements, all because electrons obey Bohr's quantized rules. This is the astonishing thing about Bohr's idea. It connects the smallest scales of matter to the larger scales of the cosmos. These same quantum jumps that produce the color of a candle flame also mark the light from galaxies millions of light years away. The laws that govern an atom in your skin are the same ones that govern the birth of stars. And yet, for all its beauty, Bohr's model was also a simplification. In reality, electrons don't orbit the nucleus like planets. They exist as standing waves, spread out like clouds of probability. But Bohr's insight was still a monumental step. It gave scientists a language for describing atomic behavior that matched experiment with elegant precision. It also gave the world a new kind of aesthetic. The idea that atoms had allowed states and forbidden zones suggested a deep harmony in nature. Electrons couldn't improvise or wander freely. They could only leap between the notes written into their structure. Electrons don't do improvisation, only precise solos. Their movements, while invisible, create the literal color of the world. Bohr's success inspired a generation of physicists to explore the strange new landscape of the quantum world. The patterns he discovered in the spectrum of hydrogen became a map for understanding the building blocks of matter. And though later theories would expand and refine his model, the heart of it remains as true today as it was in 1913. Energy is not continuous. It comes in distinct, countable amounts. Every time light flashes from a spark, every time you see the shifting colours on the surface of a soap bubble, you are watching the quiet arithmetic of energy levels. The glow of a neon sign, the twinkle of a distant star, even the way your eyes detect light, all of it depends on the same rule that Bohr set down. Electrons live in precise patterns, and light is the language they use to communicate. It is humbling to realize that the universe, at its most fundamental level, runs not on chaos, but on rhythm. Every element contributes its own tones and harmonics, its own subtle frequencies, to the grand composition of existence. The atoms that make up your body are playing too, their electrons forever shifting and humming, releasing tiny flashes of light too faint to see. If you could somehow hear them, the entire cosmos would sound like a symphony of vibration and exchange, a billion instruments playing in perfect mathematical time. And all of that began with a simple idea, that electrons are not free to go wherever they please, but must step carefully between their allowed energies. From the first spark of Planck's quantum to the structure of atoms themselves, the universe revealed that its foundation is made not of matter or motion, but of patterns, energy arranged in steps, like notes on a cosmic scale. Every atom hums a melody, and light, quite literally, is its song. By the early 1920s, the picture of the atom was beautiful but incomplete. Niels Bohr's tidy orbits worked wonderfully for hydrogen, yet when scientists tried to apply the same model to more complicated atoms, the mathematics began to fall apart. Electrons were not behaving like miniature planets after all. They seemed to exist in ways that defied location, appearing both here and there, moving and not moving all at once. The classical image of an orbiting particle, elegant as it was, simply couldn't capture their true nature. Something deeper was needed, a way of describing matter that embraced its strangeness instead of forcing it into old patterns. In 1926, an Austrian physicist named Erwin Schrödinger began to think differently. He had been fascinated by waves ever since childhood, by how vibrations on a string could form standing patterns of sound. The idea that matter itself might behave like a wave had been proposed earlier by Louis de Broglie, a French prince-turned-physicist, who suggested that every particle has a wavelength related to its momentum. It was a bold concept. Perhaps electrons didn't orbit the nucleus like tiny marbles, but flowed around it like ripples around a stone. Schrödinger decided to take that idea seriously, and to write down the mathematics that could describe it. The result became known as the Schrödinger equation, a deceptively simple formula that would change physics forever. Instead of describing electrons as points in space, Schrödinger described them as wave functions, patterns of probability that spread through space like soft, vibrating fog. The wave function didn't tell you where the electron was, it told you where it was likely to be. Its peaks represented high probabilities, its troughs low ones. The act of measurement, observing or interacting with the electron, would cause this hazy cloud of potential to collapse, revealing one concrete outcome from the many possibilities. It was an astonishing idea. The atom was not a clockwork system of moving parts, but a shimmering blur of probabilities. Within it, energy and matter merged into one seamless dance of chance and structure. Where Bohr's atom had sharp orbits, Schrödinger's atom had standing waves, continuous and elegant patterns of vibration that wrapped perfectly around the nucleus. The allowed energy levels of the atom corresponded to wave patterns that fit neatly, without overlap or interruption. Just as a guitar string can only vibrate at certain frequencies, electrons could only exist in wave forms that resonated perfectly with the space around the nucleus. This picture explained why electrons could only occupy discrete energy levels. If a wave didn't fit, it simply couldn't exist. Energy quantization wasn't arbitrary. It was the geometry of the wave itself. Bohr had described the result. Schrödinger showed the reason behind it. The beauty of this model lay not only in its accuracy but in its imagery. If we could somehow see the atom as Schrödinger did, we wouldn't find little dots circling a nucleus. We would see shapes, vast ghostly clouds with varying densities, each representing the probability of finding an electron in that region. The simplest hydrogen atom would appear as a soft sphere of mist, fading gradually into space. Higher energy atoms would form more complex patterns, dumbbell shapes, clover leaves, toroidal rings, intricate geometries of possibility that look almost like abstract art. These clouds are not static. They shimmer, shift, and merge as electrons move between states. Yet the movement isn't mechanical, it's statistical. The atom's architecture is defined by probability itself, the idea that something so concrete, the matter that makes up your body, your desk, and the world around you, could be built upon uncertainty was both thrilling and unsettling. For many physicists, including Schrödinger himself, this probabilistic nature of reality was difficult to accept. He once joked that he did not like the concept of jumping electrons or randomness in fundamental laws. But the experiments kept proving him right. Wherever scientists looked, they found that the mathematics of wave functions predicted nature's behavior with breathtaking precision. It is strange to think that the universe is built not from certainty, but from possibilities weighted by likelihood. Yet, paradoxically, this surrender of precision gave physics more power than ever. With Schrödinger's equation, scientists could predict how atoms bind together to form molecules, how materials conduct electricity, and even how stars fuse elements in their cores. Chemistry itself became an expression of wave patterns, an art of probability sculpted by energy. If you pause to picture this world, it's hauntingly beautiful. Imagine every atom around you, in the air, in the fabric, in your own skin, as a network of shimmering clouds, each one buzzing with silent potential. The space that seems empty between nucleus and electron isn't truly empty. It's filled with the hum of mathematical possibility. Those electron clouds overlap and blend, forming bonds that hold everything together. You're quite literally made of probabilities that have, for the moment, chosen to exist. In this way, the atom becomes a kind of cosmic instrument. Each allowed wave pattern corresponds to a particular energy level, a distinct note in the atom's song. When an electron transitions from one pattern to another, it emits or absorbs a photon, a musical tone of light, whose frequency matches the difference between the two notes. The colours of the world, the glow of stars, and the shimmer of metals all emerge from this grand resonance of waves and quanta. Schrödinger's theory also carried a quiet philosophical weight. It suggested that nature doesn't draw hard lines between things. Instead, it trades certainty for elegance. Instead of saying where something is, it gives us a landscape of where it could be. Reality at its core is fluid, not a series of static objects, but a continuous vibration of information and potential. This realization changed more than physics. It reshaped how humans think about existence itself. Einstein famously disliked this uncertainty, muttering that God does not play dice with the universe. But the quantum world doesn't ask for approval. It simply is, the dice roll whether we watch or not. And curiously, the randomness is not chaotic but ordered, following strict statistical laws that make the unpredictable, in a sense, predictable after all. Today, the shapes predicted by Schrödinger's mathematics can be visualized with computers, revealing a hidden architecture beneath everything. These visualizations are astonishingly intricate, layers of symmetry and geometry that rival the patterns in snowflakes or seashells. Every orbital shape, every subtle fold of probability is a product of energy finding the most harmonious way to exist. When you look around and see the solidity of the world, it's easy to forget that it's all built on uncertainty. Yet this uncertainty is what allows atoms to form bonds, molecules to flex and twist, and life to adapt and thrive. A perfectly rigid, deterministic universe would be sterile. It's the tiny flickers of chance, the wave of potential beneath every particle that make the universe alive with creativity. So, the next time you picture an atom, don't imagine little spheres whirling around a nucleus. Instead, imagine music frozen in space, stand in waves of energy resonating in harmony. Within each vibration lies the possibility of light, of matter, of everything we know. And perhaps that is the most elegant truth of all, that existence is not a thing, but a melody, a quantum wave, endlessly resonating, shaping the patterns of reality, beautiful, uncertain, and profoundly alive. In the strange world of the quantum, even the act of looking can change what you find. This isn't just poetic language, it's one of the most profound discoveries in science. In the 1920s, a young German physicist named Werner Heisenberg stumbled upon a truth so unsettling that even Einstein found it hard to accept. Heisenberg showed that nature places a fundamental limit on what can be known at the same time. The sharper you try to measure one property of a particle, the blurrier another becomes. It's called the uncertainty principle, though that word, uncertainty, doesn't quite do it justice. It isn't about human error or clumsy instruments. It's about the fabric of reality itself. Even in a perfect experiment, no amount of cleverness can break this rule. If you try to measure an electron's exact position, you lose track of its momentum. Pin it down, and its movement becomes unknowable. Watch how fast it moves, and it blurs into a smear of possibility. It's as if nature insists that precision must always be paid for with mystery. Heisenberg's idea was revolutionary. Until then, physicists assumed that if they could build better tools, they could eventually know everything about a system, exactly where every particle was and how it moved. But the quantum world refused to cooperate. At tiny scales, measurement itself becomes part of the story. To see an electron, you must shine light on it, but the photons you use to observe it also strike it, nudging it out of place. There's no way to peek without poking. Observation and disturbance are inseparable. The principle can be written in a single line of mathematics, but its meaning is far deeper than a formula. It tells us that reality is not a static picture waiting to be examined. It's an active, restless dance. Every particle jitters with intrinsic uncertainty, as though reality itself jiggles too fast for stillness. That jitter, though invisible, is the engine of everything that happens. To understand how profound this is, imagine a violin string vibrating in the dark. The exact position of the string at any moment can never be pinned down. It's constantly moving through a range of possibilities. The vibration is the music. Without that motion, there would be silence. In the same way, the universe's inability to stay perfectly still is what gives rise to energy itself. The tremble of uncertainty is what keeps existence alive. Heisenberg's uncertainty also applies to time and energy. You can't know both with perfect accuracy. The shorter the duration you examine, the less precisely energy can be defined. This isn't a flaw. It's a permission slip written into the laws of physics. For incredibly brief moments, energy can fluctuate, appearing or vanishing like sparks in darkness, as long as it balances out in the end. Nature allows these tiny loans of energy, provided they're repaid almost instantly. These momentary fluctuations are not just theoretical, they happen everywhere, constantly. Even in what we call empty space, virtual particles flicker into and out of existence, borrowing energy from nothingness and then returning it before anyone can catch them. They live for unimaginably short times, trillionths of a second, yet their presence leaves a measurable imprint. The attraction between two uncharged metal plates in a vacuum, known as the Casimir effect, arises from this restless sea of temporary particles. The vacuum, it turns out, is never truly empty. It is an ocean of potential energy and perpetual motion. When you think about it, this restlessness is comforting. The universe is not static or mechanical, but alive with activity, even in its quietest moments. Stillness, in the absolute sense, doesn't exist. Everything vibrates, everything fluctuates. Even the atoms in your body tremble with quantum uncertainty, their electrons forming shifting clouds of probability. This blurring between what can and cannot be known also forces us to rethink what it means to understand something. For centuries, science sought to describe the world in perfect detail, to measure, predict, and control. Heisenberg's discovery gently reminds us that total control is an illusion. The closer you look, the more the world slips through your fingers. But far from being a failure, this uncertainty is a source of freedom. It allows creativity, complexity, and life itself. If particles could be pinned down precisely, if the universe were perfectly predictable, nothing new could ever happen. There would be no surprises, no spontaneity, no change. The uncertainty principle ensures that the future is not carved in stone but carved in mist. It leaves room for the universe to breathe. Einstein, ever the realist, was deeply troubled by this notion. He famously remarked that God does not play dice with the universe. But quantum mechanics cheerfully replied that not only does God play dice, the dice are still rolling, everywhere, all the time. And the astonishing thing is that this cosmic randomness doesn't lead to chaos. It averages out to produce the stable, ordered world we see. From the jittering of electrons comes the solidity of matter. From chance arises pattern. You could say that the uncertainty principle is the heartbeat of quantum energy. Those tiny fluctuations, the inability of particles to sit perfectly still, are what make phenomena like zero-point energy possible. Even at absolute zero temperature, when all thermal motion has stopped, the uncertainty principle ensures there's still a faint vibration left, a whisper of energy that can never be removed. The universe, it seems, refuses to go completely quiet. This is more than an abstract scientific fact. It's a profound philosophical statement. It means that change is built into existence. The smallest building blocks of nature are restless not because they want to be, but because they must be. Reality doesn't pause. It oscillates, flickers, hums. Everything we see, every atom and star is an echo of that foundational tremble. And yet, rather than seeing this as a limitation, Heisenberg saw beauty in it. He once wrote that what we observe is not nature itself, but nature exposed to our method of questioning. In other words, the universe is a conversation, not a photograph. Each measurement we make is a question, and each answer depends on how we ask it. Think of how liberating that is. It means the world is not frozen in certainty. It's an ever-evolving story, told through possibilities. The same uncertainty that prevents us from knowing everything is what allows things to exist at all. When you sit quietly and feel the pulse of your own heartbeat, that rhythm, that alternation between presence and pause, is mirrored in the very foundations of physics. Between every moment of existence and non-existence, the universe balances itself, trembling delicately in between. Reality is not solid and still, it's alive with motion, too quick for our eyes to catch. Every atom, every field, every patch of vacuum space participates in this grand uncertainty dance, a waltz of probabilities and possibilities, spinning forever in the light of existence. And in that motion, in that shimmering imperfection, lies the most remarkable truth of all. Perfection isn't stillness, it's movement. The universe doesn't need certainty to be beautiful, only balance. By the time physicists had grown comfortable with electrons as waves of probability, another question emerged. Waves in what? If particles could behave like ripples, then something must be rippling. The idea of matter as both wave and particle was astonishing, but it was only half the story. Beneath the shimmering clouds of probability lay something deeper, something that would redefine what matter and energy even meant. This was the beginning of the quantum field revolution, a shift so profound that it quietly rewrote the foundations of reality itself. The clue came from an old friend, the electromagnetic field. Long before the quantum era, scientists had discovered that electric and magnetic forces could be described as invisible fields filling all of space. Move a charged particle, and the field changes. Disturb it, and waves of electromagnetic energy ripple outward at the speed of light. These ripples are what we call light itself. When the quantum picture arrived, physicists realized something extraordinary. Those waves weren't abstract. They were made of photons, each one a tiny packet of energy. It wasn't long before this logic expanded. If light came from oscillations in the electromagnetic field, perhaps everything came from similar fields. Every particle, electron, proton, quark, and beyond, might be just a ripple in its own invisible sea. Instead of particles moving through space like billiard balls, reality was an ocean of fields, each capable of producing the ripples we call particles. Imagine the universe as a vast overlapping collection of invisible oceans. There's the electron field, the photon field, the quark field, the gluon field, the Higgs field, dozens of them, interwoven and continuous, filling every corner of space. They're not floating in space, they are space, empty air, interstellar vacuum, the gap between your hands. All of it is thick with these unseen fields, humming quietly with potential. When one of these fields is excited, as say a teeny pulse travels through the electron field, we detect it as an electron. That's right. An electron isn't a little solid speck. It's a vibration, a localized ripple in an ever-present field that extends across the universe. Knock that ripple away, and the field remains, calm and ever ready to vibrate again. It's a radical thought, and yet the mathematics leaves no doubt. Fields are the fundamental ingredients of reality. Particles are the temporary disturbances, the excitations that rise and fade like waves on the surface of a pond. Even a single atom is a collection of synchronized vibrations, a miniature symphony of interacting fields. The photon, the particle of light, is a ripple in the electromagnetic field. The electron, a ripple in the electron field. Quarks, the building blocks of protons and neutrons, are ripples in their respective quark fields. When these fields interact, energy transfers from one to another. A photon interacts with the electron field to create light. A gluon mediates the dance between quarks inside an atomic nucleus. Every physical event, every spark, collision, or heartbeat is an exchange of energy between these invisible seas. In this view, the universe becomes less like a collection of objects and more like a grand, vibrating fabric. The familiar idea of matter as stuff gives way to something far more elegant, patterns of movement. What we perceive as solid and permanent is really the play of fields, waves appearing stable because of their rhythm. Take the Higgs field, for example. It permeates all of space, and when certain particles interact with it, they gain mass. Not because the field weighs them down, but because it resists their motion in a particular way. Without this field, there would be no atoms, no planets, no people. everything would zip through the cosmos at the speed of light, never able to slow down or clump together. You might say the Higgs field gives the universe its substance, not by adding matter, but by shaping how particles move through its quiet resistance. To visualize all this, close your eyes and imagine overlapping oceans, each one infinite, invisible, and alive with gentle motion. When they ripple, they give birth to the physical world. Where they intersect, forces arise. Where they stabilize, matter takes form. Even in the vastness of intergalactic space, where no atoms drift and no light passes, these fields remain. They cannot be switched off. Space itself is never truly empty. It's the calm surface of a deep and restless sea. This realization turned physics inside out. Instead of asking what the universe is made of, scientists began asking how it behaves. The fundamental question shifted from what is a particle to what does the field look like when it moves. Every experiment in modern particle physics, from the smallest laboratory setup to the colossal collisions inside the Large Hadron Collider, is really a way of poking these fields and watching the ripples they produce. When physicists first detected the Higgs boson in 2012, they weren't discovering a new particle so much as confirming the existence of the Higgs field itself, catching one fleeting wave crest in an ocean that had always been there. The event lasted only an instant, but it proved that the sea beneath reality is real. It's a humbling thought. The solidity of your chair, the light from your lamp, even the atoms in your body are not separate entities floating in emptiness. They're different vibrations of the same universal fabric. You are quite literally a pattern in motion, a fleeting arrangement of ripples in a cosmic sea. In this light, the old philosophical debate about matter versus energy begins to dissolve. They're not two different things at all, but two ways of describing the same underlying phenomenon. Fields are energy, structured by rules and symmetries that give rise to the diversity of the universe. When those fields ripple, we see particles. When they rest, we call it empty space. And yet, even rest is an illusion. According to quantum theory, a field can never be perfectly still. The uncertainty principle guarantees a faint vibration even in the absence of particles, a baseline hum known as zero-point energy. It's as if the universe cannot bear silence. Even in perfect darkness, something moves. Quantum field theory, the framework that unites all these ideas, is arguably the most successful theory in science. It predicts the behavior of particles to astonishing precision, sometimes to more than 10 decimal places, and yet it carries a strange serenity, an almost spiritual elegance. It says that the entire universe, from galaxies to atoms, emerges from a single continuous fabric of fields, endlessly weaving and unweaving themselves. When you begin to picture the world this way, solidity and emptiness lose their meaning. Every surface, every star, every breath is a ripple in something larger, invisible and profoundly connected. There is no true separation, only patterns interacting across an ocean of potential. Matter, then, is not made of stuff. It's made of structure, of rhythm and resonance, of movement in the dark. The universe is less a machine and more a melody, played in the language of fields, and so, when you look at your hand, or a falling leaf, or the distant shimmer of starlight, what you're really seeing is the same thing in countless forms. The quiet, endless motion of invisible oceans overlapping through everything. Matter is not made of things. Matter is made of motion. Matter is not made of stuff, but of patterns moving in the dark. If you could somehow strip the universe of all its stars, dust, planets, and atoms, if you could remove every photon of light and every whisper of heat, you might think you'd be left with absolute nothingness, a silent, empty void. But quantum physics tells a different story. In the quantum view, even the deepest vacuum isn't truly empty. It seethes with activity, a restless sea of invisible motion. Beneath the calm surface of space lies a constant shimmer of creation and annihilation, a whisper of energy that can never be silenced. This background hum of existence is called zero-point energy, the lowest possible energy a system can have. It's the ground note of the universe, the energy that remains even when everything else has been taken away. Classical physics imagined that if you cooled something down enough, you could stop all motion entirely. But quantum theory says otherwise. Even at absolute zero, when all thermal energy is gone, particles and fields continue to quiver with subtle vibrations. The universe, it seems, cannot stand still. These tiny fluctuations come from the uncertainty principle itself. Remember that position and momentum can't both be known precisely. If a field were completely motionless, its energy and its rate of change would both be exactly defined, something quantum mechanics forbids. So the field must always have a little motion left, a little uncertainty. It wobbles, even in nothing, and that perpetual wobble gives the vacuum its faint but irreducible energy. To visualize it, imagine trying to calm a bowl of jelly so that every ripple disappears. You can wait as long as you like, but even the tiniest vibration, a passing sound wave, a whisper of gravity, will stir it again. The vacuum of space behaves the same way. It quivers with microscopic ripples of energy that can never be fully smoothed out. These ripples have real, measurable effects. Quantum fields are constantly creating pairs of virtual particles, tiny flashes of matter and antimatter that appear, borrow a bit of energy, and vanish almost instantly. They're called virtual because they don't last long enough to become real, stable particles, but for the briefest instant they affect the world around them. They tug on nearby atoms, shift the paths of electrons, and even influence the forces between objects. One of the strangest proofs of this invisible motion came in the 1940s with a Dutch physicist named Hendrik Casimir. He imagined placing two perfectly smooth metal plates extremely close together, just a few billionths of a meter apart, and wondered what would happen. According to classical logic, nothing should occur. After all, the plates are uncharged, the vacuum between them empty. But Casimir's calculations told a different story. The quantum fluctuations in the vacuum would behave differently between the plates than outside them. Only certain wavelengths of virtual energy could fit in that narrow gap, meaning there would be slightly less vacuum energy inside than outside. The result? The plates would be pushed together, not by any mechanical force but by the pressure of empty space itself. This became known as the Casimir effect, one of the most striking demonstrations that nothing is far from empty. Later experiments confirmed Casimir's prediction with remarkable accuracy. Even in the quietest void humans can create, the vacuum pushes back. It's almost paradoxical, emptiness exerting force. And yet, once you understand that the vacuum is not absence but presence, the paradox fades. The fields that fill all of space are never at rest. Their endless fluctuations mean that the universe, at its foundation, is more like a simmering pot than a still pond. Zero-point energy is more than just a scientific curiosity. It touches some of the deepest mysteries in cosmology. When astronomers observe distant galaxies, they find that the expansion of the universe is accelerating, as though something invisible is pushing everything apart. They call this phenomenon dark energy. No one knows exactly what it is, but one idea is that it might be the energy of the vacuum itself, the accumulated effect of all those microscopic fluctuations. If that's true, then the very fabric of space carries an energy so vast and diffuse that it shapes the fate of the cosmos. Here's the astonishing part. When physicists try to calculate how much zero-point energy should exist in empty space, the numbers they get are enormous, far greater than what observations allow. In fact, the predicted value is off by an almost unimaginable factor, sometimes described as one followed by 120 zeros. That's the biggest mismatch between theory and experiment in all of science. It suggests that something profound is missing from our understanding of how the vacuum behaves. The universe seems to hold just enough of this invisible energy to drive its expansion, but not nearly as much as our equations expect. It's as though the cosmos is balanced on a knife's edge between stillness and explosion, choosing harmony over chaos. Even so, the principle stands. There is no true void. The vacuum hums with fluctuations, borrowing and repaying energy on scales too small and too fast for direct observation. These ephemeral processes underpin everything, from the forces between atoms to the stability of matter itself. Without them, the world as we know it could not exist. In a way, the vacuum's restlessness mirrors the balance between chaos and order that defines nature at every level. Just as the surface of the ocean hides countless unseen currents, the apparent calm of empty space conceals ceaseless motion. Every photon, every electron, every atom is built upon this background hum. The universe's quiet moments are not silent. They are filled with the faint vibration of possibility. If you could somehow listen to that vibration, not with your ears, but with a sense tuned to energy, you might hear a faint, omnipresent murmur. Not a sound, but a rhythm, a cosmic pulse that's been playing since the birth of time. That hum is the zero-point energy of the vacuum, a reminder that nothingness itself is fertile. It contains the seeds of everything that has ever existed or will exist. Philosophically, this reshapes the old notion of nothing. In everyday language, nothing means absence, the lack of anything at all. But in physics, nothing is an active participant. It's a stage that vibrates with hidden energy, ready to create particles at a moment's notice. When we say the universe sprang from nothing, perhaps we mean it sprang from this restless vacuum, a nothing that was already humming with potential. It's humbling to realize that even the emptiness between galaxies isn't empty. Every cubic centimeter of space, no matter how dark or desolate, holds this background of energy. It's the ultimate paradox. The quieter the universe seems, the more alive it becomes. You can think of zero-point energy as the softest possible whisper of existence. It doesn't build atoms or radiate light. It simply is. It fills every corner of the cosmos with a baseline vibration, a reminder that reality never turns off. And from this quiet, trembling foundation, everything else emerges: matter, energy, stars, and even thought. So the next time you look at the night sky and imagine the vast emptiness between those distant points of light, remember this: that emptiness is alive with motion. Invisible fields ripple, virtual particles flicker, and energy flows silently in and out of existence. Nothingness, it turns out, hums with more life than silence can hold. Whenever a scientific discovery captures the imagination, myths are never far behind. The idea of quantum energy, those endless ripples in empty space, has inspired not just physicists, but dreamers, inventors, and the occasional conspiracy theorist. After all, if even the vacuum of space is brimming with energy, surely that means limitless power waiting to be tapped. The thought is intoxicating, an infinite source of clean energy, drawn from nothing itself, fueling cities, curing scarcity, freeing humanity from its dependence on the finite. It sounds poetic, noble, and far too good to be true. The misunderstanding often begins with a kernel of real science. As we've seen, the quantum vacuum isn't empty. It teems with zero-point energy, a ceaseless background hum that can never be switched off. Measurements and experiments confirm its presence in subtle ways, through effects like the Casimir force and the stability of atoms. So it's no surprise that the imagination leaps from there to the notion of harnessing that energy, of dipping a cup into the infinite sea of the vacuum. After all, if the energy is everywhere, why can't we use it? The simple, unsatisfying answer is that nature doesn't allow it. Quantum mechanics may grant a restless vacuum, but it also enforces balance with ruthless precision. The zero-point energy of space is a kind of baseline, the lowest possible level of energy that the universe permits. You can't build a machine that extracts work from it, for the same reason you can't build a water wheel that turns in a perfectly calm pond. There's no net flow to harness, no difference, no gradient, and without a difference in energy, there's nothing to drive motion. In physics, this rule is called the conservation of energy, one of the most reliable principles ever discovered. Energy can neither be created nor destroyed. It can only change form. The dream of infinite, free power from the vacuum would require breaking that rule. It would mean drawing more energy out than was put in, getting something for nothing. And the universe, elegant though it is, does not give out freebies. To imagine why, think of zero-point energy as the ground floor of reality's building. It's the lowest level possible. You can only extract useful work by moving downhill from a higher level to a lower one, like water flowing through a turbine. But zero-point energy is the basement, the bottom of the cosmic well. You can't dig beneath it. You can't go lower. Every process we know of depends on differences between high and low energy states, hot and cold, charged and uncharged, moving and still. The quantum vacuum, for all its shimmering beauty, doesn't have that contrast. It's perfectly balanced, and that balance is precisely why everything else can exist upon it. Still, the idea persists, and perhaps it always will. There's a deep romance in the notion of hidden, limitless energy, an echo of humanity's eternal wish to transcend limitation. It has appeared in countless guises over the centuries: alchemists, philosophers, stones, perpetual motion machines, mysterious, etheric forces, and now zero-point generators. Each generation rediscovers the dream, dresses it in the language of its time, and hopes that this time perhaps the laws will bend. And yet, those very laws are what give the universe its coherence. Without conservation, without limits, there would be chaos. If energy could appear from nowhere, the delicate balances that make stars shine and atoms stable would collapse. Physics would lose its poetry because everything would be arbitrary. The constancy of natural laws, those quiet boundaries around possibility, are what make the universe intelligible and beautiful. That's not to say humanity hasn't tapped extraordinary energy sources before. The sun itself runs on quantum principles, nuclear fusion made possible by the strange dance of tunneling particles and quantum probability. It converts matter into light with breathtaking efficiency, and even that process is constrained by physics. It follows the rules precisely, wasting nothing, creating balance where chaos might have been. Quantum energy isn't infinite power waiting to be unleashed. It's the steady hum that keeps the cosmos in harmony. Some modern discussions of zero-point energy in popular culture blur this line, using the phrase as a synonym for limitless energy source or mystical force. You'll find it in movies, speculative articles, and late-night radio shows about hidden technologies. It's a captivating idea. How could it not be? But it's not what quantum physics describes. The zero-point energy of space is a property of fields themselves, not a resource to be mined. It's part of the structure, not a prize waiting to be collected. Even scientists, when they first encountered the immensity of vacuum energy in their equations, were startled by its implications. Calculations suggested that if one could somehow release even a fraction of it, the amount would be staggering. But there's the trick. It cannot be released. It's not stored energy, it's intrinsic energy. It's not potential power waiting to be used. It is the baseline upon which all power depends. In a way, it's comforting that we can't exploit it. The vacuum's untouchable energy means that the universe remains stable. If we could drain it, we might unravel existence itself. The same hum that seems like wasted potential is what holds everything in place. When you think about it like that, the dream of infinite extraction feels less like a promise and more like a misunderstanding of beauty. The laws of physics don't deny us wonder, they create it. They are the reason why the world can be understood, why energy flows predictably, why matter coheres. If you hold a glass of water and let it sit on a table, gravity pulls it down, and the table pushes back with equal force. Nothing happens because the forces balance. The vacuum's energy is like that, a perfect equilibrium. To get useful work, you'd have to unbalance it, but the moment you try, the universe pushes back. Every attempt to tilt the scales only proves how finely tuned they already are. There's a quiet dignity in those constraints. They tell us that even in a universe bursting with energy, not all of it is ours to command. The boundaries of possibility are not obstacles, they are the architecture of existence. They make life possible, and they give meaning to effort. So while the idea of limitless free quantum power is appealing, it's the limits themselves that make the real story extraordinary. We can admire the hum of zero-point energy, feel awe at its presence, and still respect the cosmic balance that keeps it beyond our reach. In the end, that's perhaps the most beautiful lesson quantum physics offers. That wonder doesn't depend on fantasy. The truth is already strange enough, vast enough, miraculous enough. We don't need to break the rules to feel amazed by the world. The rules themselves are astonishing. Reality, with all its boundaries and constraints, is not disappointing. It's believable, and it's in that believability that its beauty truly lies. Reality's constraints make its beauty believable. For most of human history, matter and energy seemed like two entirely different things. Matter was solid, tangible, the stuff you could touch. Energy was motion, heat, or light, something you could feel but never hold. But in the early years of the 20th century, Albert Einstein revealed that this distinction was an illusion. He showed that matter is energy, condensed and confined into a stable form. It was one of the simplest and most profound revelations in science, captured in a short, deceptively gentle equation: energy equals mass times the speed of light squared. That little relationship, E equals mc squared, tells us that mass and energy are two sides of the same coin. You can think of mass as energy that has slowed down enough to become tangible. The speed of a light squared is the conversion factor, a reminder of just how much energy is bound up in even the smallest bit of matter. A single gram of material, about the weight of a paperclip, holds enough potential energy to power a city for days if it could all be released at once. It's worth remembering that Einstein didn't begin with grand explosions or cosmic theories. He started with the principle of relativity, the idea that the laws of physics are the same for all observers, no matter how they move. From that, he realized that energy and mass must be connected. A moving object gains energy, and therefore, by definition, gains a little mass. Likewise, if it loses energy, its mass must decrease. The two are inseparable. Energy can take the shape of matter, and matter can melt back into energy. At first glance, this might sound abstract, but nature demonstrates it every day. Deep within the sun, hydrogen atoms fuse together to form helium, and in that process, a small portion of their mass vanishes. It doesn't disappear into nothing. It becomes light and heat streaming out across space to warm the planets. The energy we feel from sunlight is literally the lost mass of hydrogen, transformed into radiant energy. This process works in reverse too. Energy can condense into matter given the right conditions. When two photons, particles of pure light, collide with enough energy, they can give birth to a pair of particles, an electron and its opposite twin, a positron. This is called pair creation. It's as if the energy of light becomes so intense that it curls in on itself, solidifying into matter. The electron and positron spin away from each other, mirror images made from nothing but energy. But this is a temporary existence. When those two particles meet again, they annihilate each other, releasing the exact same amount of energy they borrowed from the photons in the first place. In that instant, matter dissolves back into light. Creation and destruction, material and immaterial, all part of the same continuous cycle. It's almost poetic how symmetrical it all is. The universe behaves like a careful accountant, keeping its books perfectly balanced. No energy is ever truly lost. It only changes its form, flowing between being and non-being like a tide. This balance is what allows stars to burn, atoms to exist, and galaxies to glow. When you touch a solid object, say a stone or a piece of metal, it feels permanent, solid, and unmoving. Yet, if you could look deep enough inside, you'd see that solidity is simply energy holding its breath. The particles that make up that object are in constant motion, vibrating, exchanging photons and binding together through electromagnetic energy. The matter you touch is really just energy in a tightly bound configuration, stable but restless at the smallest scales. This realization changes how we see everything. The boundary between what is and what happens begins to blur. A mountain, a beam of light, a breath of air. They're all manifestations of the same universal currency, energy. Matter is just energy that's been captured and given structure by quantum rules. The idea of turning energy into matter and back again might sound like science fiction, but it's happening everywhere, all the time. Cosmic rays striking Earth's atmosphere generate bursts of particle pairs from pure energy. Inside particle accelerators, scientists recreate these processes at will, smashing high-energy photons together to briefly conjure new particles into existence. Each creation and annihilation tells the same story, the dance of energy and form, endlessly repeating since the dawn of time. Even the universe itself seems to have been born from this principle. In the beginning, moments after the Big Bang, everything that would one day become stars, planets, and people existed as pure energy, a glowing plasma of light and motion. As the cosmos expanded and cooled, energy condensed into matter, forming the first particles, the first atoms, the first galaxies. You could say that all of existence is light slowed down and shaped by the quantum fabric of reality. If that sounds mystical, it's only because it's so deeply true. The chair you're sitting on, the screen you're looking at, and the air you breathe are all made of energy that's been caught in the gravitational and electromagnetic choreography of the universe. Matter isn't the opposite of energy, it's energy in costume. This perspective also explains why so much energy can be released when matter is destroyed. In nuclear reactions, both fusion in stars and fission in reactors, small differences in mass become enormous amounts of energy. That's because the conversion factor in Einstein's equation involves the speed of light squared, a number so large that even a tiny amount of mass translates to staggering energy. When atoms fuse or split, the bonds that hold them together rearrange, and that difference manifests as light and heat. But while it's tempting to see this as a source of endless power, the same conservation laws apply here too. The universe gives energy only in exchange for structure, never for free. For every transformation, there is an equal cost. The grandeur of E equals mc squared isn't in its potential for power, but in its grace, the symmetry of how matter and energy sustain one another. You might imagine the cosmos as a vast sculpture made entirely from frozen light, a work of art carved by the laws of quantum mechanics. The atoms in your body were once pure energy released from ancient stars. That same energy, billions of years from now, may find new form as some other pattern, another heartbeat in the cosmic rhythm. There's a quiet reassurance in knowing that nothing truly vanishes, even when stars collapse, when matter burns away, or when you let go of something precious. The energy that composed it remains. It changes, travels, and takes on new shapes, but it never ceases to be part of the great cycle. At its core, Einstein's revelation wasn't just about equations. It was a reminder that the universe is unified, that all the dazzling variety we see is woven from the same luminous thread. Matter and energy are not separate realms, but two faces of the same infinite coin. So the next time you look at sunlight streaming through a window, remember, that light is kin to every atom in your body. It's the same essence, vibrating at a different tempo. The universe, from the smallest grain of sand to the brightest star, is a continuous exchange of energy becoming matter, and matter returning to energy. Solidity is simply energy holding its breath, a fleeting moment of stillness in the eternal dance of transformation. In the everyday world, barriers are absolute. A wall stops a ball, a table holds a cup, and a locked door remains shut unless you open it. But in the quantum world, the rules are far more forgiving, or, depending on how you see it, far more mischievous. Down there, particles sometimes slip through barriers they should never be able to cross. They don't crash through or break them down. They simply appear on the other side, as if the obstacle were only half real. This strange behavior is known as quantum tunneling, and it's one of the most counterintuitive yet essential phenomena in physics. Without it, the sun wouldn't shine, electronics wouldn't work, and the universe itself might look very different. It's the quiet art of defying the impossible. not through force, but through probability. To understand tunneling, imagine a ball rolling toward a hill. In the classical world, if the ball doesn't have enough energy to climb over the top, it simply rolls back. There's no middle ground. Either it has enough energy or it doesn't. But in the quantum world, the ball isn't a solid object. It's a wave, a spread out cloud of probability describing where it might be. When that wave hits a barrier, part of it bounces back, but another part seeps through, like a faint echo on the other side. This isn't magic or teleportation, it's the mathematics of waves. The quantum wave doesn't stop neatly at the wall, it fades gradually, and in that fading, there's always a small chance that it continues beyond the barrier. If you wait long enough, you might find the particle has tunneled through. The higher or thicker the barrier, the smaller the chance, but never zero. At the quantum scale, even walls have a soft-hearted side. It's a wonderful thought, really. Nature allows for a little flexibility, a little forgiveness. What seems impossible from one perspective becomes merely improbable from another, and in a universe built on probabilities, improbabilities happen all the time. One of the most spectacular examples of tunneling takes place in the hearts of stars. In the core of the Sun, hydrogen nuclei, protons, are constantly trying to fuse together to form helium. But there's a problem. Each proton carries a positive electric charge, and like charges repel. To get close enough to fuse, they would need to overcome a tremendous barrier of electrostatic force. The temperatures inside the Sun, though immense, aren't quite high enough to make that happen by brute strength alone. Yet fusion happens anyway, billions of times every second. How? Because of tunneling. The proton's quantum waves overlap, and occasionally, a proton's wave leaks through the energy barrier. The particle borrows just enough probability to find itself on the other side, where it can fuse with its partner. Without this loophole in nature's rules, the Sun would be dark and life would never have begun. Every ray of sunlight that touches your face is a quiet testament to quantum tunneling at work. The same principle explains another mysterious process, alpha decay, the way some heavy atoms naturally shed particles over time. Inside the nucleus of an unstable atom, clusters of protons and neutrons, called alpha particles, sometimes find themselves trapped by the strong nuclear force. They don't have enough energy to escape, at least not classically. But their quantum wave extends beyond the boundary of the nucleus, and every so often part of that wave makes it through. When it does, the alpha particle appears outside, carrying energy with it. It's as if the nucleus occasionally sighs, letting go of a tiny piece of itself through sheer quantum chance. Tunneling isn't confined to the realm of stars and nuclei. It's woven into the technology of everyday life. The modern world runs on semiconductors, the delicate materials that form the heart of computers and smartphones. Inside these materials, electrons move through barriers that should, by classical logic, stop them cold. Quantum tunneling allows them to flow through specific regions, creating the precise behavior that engineers design into transistors and diodes. The reason you can listen to music, read this sentence, or send a message halfway around the world is that electrons, at the smallest scales, are unbothered by human definitions of impossible. There's even a type of microscope, the scanning tunneling microscope, that uses this effect to feel the positions of individual atoms. A sharp metal tip hovers just above a surface, and electrons tunnel between the tip and the atoms below. By measuring that current, scientists can map the surface with astonishing precision, revealing not just molecules, but the patterns of their quantum states. The device that lets us see the invisible works only because particles can slip through barriers. When tunneling was first proposed, even seasoned physicists found it difficult to believe. The idea seemed absurd. How could something cross a gap without going over it? But experiments quickly confirmed it. Quantum particles do not obey the binary logic of yes or no. They live in the in-between, guided by probabilities that can never quite reach zero. The world, it turns out, isn't built from absolutes. It's built from chances. That might sound chaotic, but it's precisely the opposite. Quantum tunneling is not a violation of laws, it's a consequence of them. The rules of wave mechanics predict it perfectly. It happens not in spite of order, but because of it. The universe allows for a little randomness at the smaller scales, and out of that randomness come stars, chemistry, and life. There's something quietly poetic about this. The same principle that powers our sun also powers our electronics. The same rule that lets light escape from the heart of atoms also lights the modern world. Every tunnel, from the atomic to the astronomical, tells the same story. That possibility is never fully extinguished. It's easy to think of tunneling as strange or abstract, but it reflects something deeply natural, the idea that even boundaries have texture. In the quantum world, barriers are more like membranes than walls, soft enough for possibility to seep through. If particles can tunnel through energy barriers, perhaps it's no wonder that stars can burn for billions of years, and that life, built from improbable chemistry, can persist against the odds. When you zoom out and think of it this way, tunneling becomes less of a curiosity and more of a quiet act of generosity from the universe. It's nature's way of saying, you may pass, even when reason says you shouldn't. And it's through this act, this improbable crossing of invisible walls, that the cosmos powers itself. The energy of stars, the birth of elements, the light that reaches us across the void, all of it depends on tunneling. It's a reminder that sometimes even the smallest chance is enough. At the quantum scale, even walls have a soft-hearted side, and through that softness the universe keeps its fires burning. At the heart of every star, far beneath its glowing surface, there's a quiet miracle happening, one that depends entirely on the strange generosity of quantum physics. Deep in those cores, under pressures and temperatures beyond human imagining, atoms are engaged in a constant struggle between repulsion and attraction. Each atomic nucleus is positively charged, and like all positive charges, they push each other away with fierce determination. By every law of classical physics, they should never come close enough to fuse, and yet somehow they do. This paradox lies at the center of creation itself. Every glimmering point of light in the night sky, every sunrise that warms the earth, every flicker of life that depends on that warmth, all of it exists because of a delicate quantum trick called tunneling. Inside the core of a star like the Sun, hydrogen atoms are squeezed together under crushing pressure. The temperature there reaches around 15 million degrees Celsius, hot enough for the atoms to move at tremendous speeds. Still, their electrical repulsion should keep them apart. The energy they carry simply isn't enough to overcome the barrier between them. But in the quantum world, barriers are never absolute. As we've seen, particles are not little solid spheres. They are waves of probability, and those waves can overlap. When two protons in a star's heart come close enough for their quantum waves to mingle, there's tiny chance, a 1 in a billion kind of chance, that they will tunnel through the barrier and merge. When that happens, they release a flash of energy and form a new element, helium. The process is astonishingly rare for any single pair of protons, but there are an unimaginable number of them in a star's core. This is what powers the stars. Quantum tunneling, invisible and unstoppable, allows matter to fuse where classical physics says it shouldn't. It's the spark that keeps the universe alight. Each time two protons successfully fuse, a small portion of their combined mass is lost, transformed into energy according to Einstein's famous equation, energy equals mass times the speed of light squared. That energy radiates outward, bouncing between countless particles, slowly working its way to the surface over thousands of years before finally escaping into space as starlight. The glow that reaches your eyes tonight might have begun its journey long before recorded history, born in a quiet quantum event deep within the sun's heart. If you could somehow stand at the core of a star, not that you'd survive long enough to admire it, you'd see a world of perpetual creation. Particles dart and collide, quantum waves overlap, and in each instant, the improbable becomes inevitable. It's a vast, humming sea of light in the making. What's remarkable is not just that this happens, but how perfectly balanced it is. If quantum tunneling were even slightly more likely, stars would burn through their fuel too quickly, flaring out in short-lived bursts. If it were slightly less likely, fusion would rarely happen at all, and the cosmos would be cold and dark. Instead, it sits delicately in between, enough to light the universe, but slow enough to let it endure for billions of years. This improbable balance is the reason we have time, warmth, and life. Over those billions of years, fusion does more than produce light. It creates the elements themselves. The universe began with almost nothing but hydrogen and helium, the simplest building blocks. But inside stars, those simple atoms are forged into heavier ones: carbon, oxygen, nitrogen, and beyond. In the most massive stars, fusion continues through layers of elements, stacking one atop another like the rings of an onion, until iron forms at the center, the end of the line for fusion's efficiency. When those massive stars finally die, their cores collapse and explode in titanic supernovae, scattering their forged elements across the cosmos. Every atom heavier than hydrogen or helium, including the calcium in your bones, the iron in your blood, and the carbon in your DNA, was once part of a star's heart. Those elements travelled across space for millions or even billions of years before becoming part of planets, oceans, and eventually you. It's humbling to realize that every living thing, every rock, every drop of water is a product of this process. The quiet labour of countless stars transmuting matter through quantum fire. The sun that warms your face today is part of that same story, a continuation of a lineage stretching back to the first stars that ever burned. And yet, for all its grandeur, the process itself depends on something as subtle and uncertain as quantum tunneling, the faint overlap of probability waves inside an atom. From the outside, a star seems fierce, violent, and burning. But inside, its light is born not from violence, but from delicate chance. It's not brute force that powers the cosmos, but a whisper of probability. The universe's gentle willingness to let the impossible happen once in a while. You can think of a star as an enormous self-sustaining quantum engine. Its heart converts matter into light through processes that depend on both relativity and quantum mechanics, the two great pillars of modern physics. Without the interplay of both, the star would fail. Relativity explains how mass becomes energy, while quantum mechanics explains how it happens at all. Each photon that escapes a star carries a story of those laws working in harmony, the smallest scales shaping the grandest outcomes. As that light spreads through the cosmos, it becomes the lifeblood of galaxies, fueling the chemistry of planets and the growth of living things. The warmth you feel on your skin from sunlight is ancient energy, born billions of years ago in an atomic embrace that defied the odds. That same quantum spark continues to flow outward, touching everything it meets, connecting all things in an invisible chain of energy and time. When you look up at the night sky, you're not just seeing distant points of light. You're looking at the ongoing story of quantum mechanics playing out on a cosmic scale. Each star is a living reminder that the rules governing the smallest particles can create the most magnificent structures. The dance of uncertainty at the heart of atoms has scaled up to illuminate galaxies. It's a beautiful irony that the universe's greatest certainty, the steady light of the stars, arises from its smallest uncertainty. The trembling of particles, the flicker of quantum probability, becomes the glow that fills the heavens. And perhaps that's the quiet lesson behind it all, that fragility and endurance aren't opposites. The most enduring light in the universe comes from the most delicate process imaginable. From trembling probabilities comes the strength to shine for billions of years. The next time you watch the sunset or trace the path of a star across the night, remember that its light began as a quantum whisper. It tunneled through barriers that should have stopped it, burned for eons in perfect balance, and crossed the cold expanse of space to reach you. You are, in a very real sense, the cooled ash of quantum fire, shaped by the fusion of stars bound by the same laws and glowing still with the borrowed light of the cosmos. If the universe could take a deep breath, it would never exhale. Instead, it would keep expanding, forever stretching the fabric of space itself wider and wider. That is quite literally what it's doing right now. Every distant galaxy is moving away, and the farther it is, the faster it recedes. What's stranger still is that this expansion isn't slowing down with time, it's speeding up. Space isn't just growing, it's accelerating outward, as if something invisible were gently pressing the cosmic gas pedal. That invisible something is what scientists call dark energy, an unseen pressure that permeates the cosmos, driving everything apart. It doesn't shine, it doesn't clump, and yet it dominates the universe. Roughly 70% of all the energy in existence is dark energy, and though we can measure its effects, its nature remains one of the greatest mysteries in science. To understand where dark energy might come from, we need to return once more to the quantum vacuum, that restless sea of invisible energy we've already met. Even in absolute emptiness, quantum fields are never still. They flicker, shift, and hum with zero-point energy. It's tempting to think that this endless background activity could explain the universe's acceleration, that the vacuum's own energy is what pushes space to expand. This idea isn't new. In fact, it first appeared in the early 20th century in the equations of Albert Einstein himself. When Einstein formulated his general theory of relativity, the description of how gravity bends and shapes space, he found that the universe should naturally be expanding or contracting. But at the time, astronomers believed the cosmos was static, unchanging. To fix that, Einstein added a term to his equations, the cosmological constant. This constant acted like a built-in pressure of space itself, a kind of cosmic anti-gravity that could hold the universe in balance. A few years later, Edwin Hubble's observations revealed that the universe was expanding after all, and Einstein reportedly called his cosmological constant the greatest blunder of his career. Yet, decades later, when scientists discovered that the expansion of the universe was accelerating rather than slowing down, Einstein's so-called blunder suddenly looked prophetic. The cosmological constant was reborn, this time as a way to describe dark energy. In modern physics, the cosmological constant is often interpreted as the energy of empty space, the vacuum energy predicted by quantum field theory. Every quantum field, even when stripped of all particles, has a residual energy that cannot be removed. Add up all those tiny zero-point contributions from every field in the universe, and you'd expect a colossal vacuum energy density, one so enormous it would blow the universe apart instantly. But when physicists actually compare those theoretical predictions to what we observe, there's a staggering mismatch. The numbers differ by a factor of roughly 1 followed by 120 zeros, perhaps the most embarrassing discrepancy in all of science. Somehow, the real vacuum energy is incredibly small, yet not zero, just small enough to let the universe expand slowly, gently, gracefully, instead of tearing itself apart in an instant. It's as if the cosmos has tuned itself with exquisite precision, balancing on the edge between stillness and explosion. You might picture it like a calm ocean that, despite being vast and deep, only ripples slightly at the surface. Beneath that stillness, unimaginable energy swirls unseen. Every cubic centimetre of space, even in the void between galaxies, contains this hidden hum, a faint residue of quantum activity that quietly shapes the destiny of everything. As space expands, it doesn't dilute that energy. Instead, the vacuum energy stays constant per unit of volume. So as the universe grows, there's more space for that energy to fill, and the total amount of dark energy increases. The result is a feedback loop. More space means more dark energy, and more dark energy means faster expansion. It's a gentle, unstoppable acceleration that stretches galaxies ever farther apart. Eventually, if this continues indefinitely, distant galaxies will vanish from view, slipping beyond the reach of light itself. The night sky will grow emptier over trillions of years, until only the nearest galactic neighbours remain visible. Future observers, if there are any, might never know that other galaxies ever existed. The expanding universe will quietly erase its own history. That may sound melancholic, but there's beauty in it too. The same vacuum energy that drives galaxies apart is also the reason the cosmos remains dynamic and alive. Without it, gravity might have pulled everything back together long ago. Instead, space itself stretches, powered by its own hidden energy, a quiet pulse woven into the fabric of existence. In a sense, the universe is both growing and resting at once. The galaxies drift apart, but within them stars are born, planets form and life unfolds. The expansion doesn't disturb local structures. It only stretches the space between them. From our small vantage point, the cosmos feels still, yet on a grand scale it's a living, breathing entity. Scientists continue to search for the true nature of dark energy. It might be a true cosmological constant, a fixed property of space itself, or it could be something dynamic, an evolving field that changes over time. Some theories even suggest that dark energy could one day weaken or reverse, leading to a big crunch, or grow stronger, tearing galaxies, stars and atoms apart in a big rip. For now, the evidence points toward constancy, a steady cosmic hum that has been present since the beginning. It's humbling to realize that what we call nothing may be the most powerful something of all. The vacuum, once dismissed as empty, has turned out to be a creative force, birthing particles, influencing gravity, and shaping the universe's fate. It's as if reality itself rests on an invisible ocean of energy, endlessly calm yet infinitely deep. Perhaps, in a poetic sense, dark energy is the universe's way of maintaining balance. Stars burn out, galaxies fade, but space itself carries on, quietly expanding, endlessly renewing. It's not an explosion, but a slow breath, an eternal unfolding that requires no fuel and no direction. When you look up at the night sky, every pinpoint of starlight exists against that expanding backdrop. The galaxies are not just drifting through space, the space between them is growing, and though we can't see the force behind it, we can feel its echo in the patterns of cosmic light, in the faint afterglow of the Big Bang, and in the very structure of the universe itself. In the end, dark energy reminds us that even the emptiest places are not truly empty. Space is not a void, but a medium, a silent fabric that hums with hidden energy. The same quantum fields that once gave rise to particles and light now shape the grandest architecture of the cosmos. The universe doesn't expand into anything. It expands within itself, carried outward by the invisible tide of its own being. Space itself stretches, powered by its own hidden energy. And in that slow, ceaseless motion, the cosmos keeps time with a rhythm older than stars, softer than silence, and deeper than imagination. Every galaxy, every cluster of stars, every breathtaking swirl of cosmic structure you see in the night sky, all of it began as a whisper, a tremor, a tiny, unpredictable fluctuation in an almost perfectly uniform early universe. If you could have seen the cosmos in its infancy, it would have looked like a smooth, glowing mist of energy, expanding rapidly, almost featureless. And yet, hidden within that calmness, quantum physics was quietly sketching the outlines of everything that would one day exist. The early universe was a restless place, a frothing sea of energy fields flickering in and out of equilibrium. Quantum mechanics tells us that even in perfect emptiness, energy cannot be completely still. There's always a bit of jitter, a tiny, unavoidable uncertainty in how much energy any given region of space holds. These are called quantum fluctuations, and they are the smallest imaginable irregularities, smaller than atoms, smaller even than the particles that make atoms. On their own, such fluctuations would seem meaningless, random jitters that average out to nothing. But in the first fractions of a second after the Big Bang, something extraordinary happened. The universe itself underwent a sudden burst of expansion known as cosmic inflation. Space expanded faster than light, not moving through space, but stretching space itself, inflating these tiny quantum ripples to cosmic scales. The minuscule bumps in energy became vast regions with slightly more or less matter than their neighbours. It's astonishing to realise that the grand architecture of galaxies began as quantum noise, the universe's own fidgeting, magnified across eternity. Galaxies are what happens when the universe can't stop fidgeting. Once inflation ended, the universe continued to expand, but more slowly. The energy from inflation transformed into particles and radiation, the hot plasma of the early cosmos. The regions that were ever so slightly denser began to attract more matter through gravity, while slightly thinner regions lost some. Over millions of years, this imbalance grew. What started as a difference of 1 part in 100,000 became the first cosmic structures, clusters of gas that would cool, collapse, and ignite as stars. In a way, galaxies are fossils of quantum physics. Their shapes, their distributions, their very existence trace back to random fluctuations in an otherwise smooth sea of primordial energy. Every spiral arm of stars, every glowing nebula, every planet that would someday circle a sun, all of it can be traced to those original quantum ripples. We have a snapshot of that moment frozen in the sky, the cosmic microwave background. It's the faint afterglow of the Big Bang, a wash of ancient light that fills the universe. When we look at it with sensitive instruments, it appears remarkably uniform, the same in every direction, to better than 1 part in 100,000. But those tiny variations, that faint mottling of brightness, are the fingerprints of those ancient quantum fluctuations. Scientists map these patterns with incredible precision. From them, they can infer the conditions of the early universe, the rate of its expansion, and even the seeds of its future structure. Each faint patch of extra warmth corresponds to a slightly denser region, which would one day become a galaxy or a cluster of galaxies. In those maps, you can almost see the universe's first daydreams, delicate hints of what it would grow into. It's hard not to be amazed by the scale of the transformation. Quantum fluctuations are unimaginably small, a billionth of a meter. Galaxies, by contrast, stretch for hundreds of thousands of light years. Between those extremes lies a bridge built by cosmic expansion and time. The universe took microscopic irregularities and turned them into the vast cosmic web we see today, an interconnected network of filaments and voids stretching across billions of light years. The logic behind it all is simple, yet profound. Gravity pulls, it amplifies differences. Where there's a little more matter, gravity draws in even more. Where there's a little less, gravity lets matter drift away. Over time, the small becomes large, the faint becomes bright, and the random becomes meaningful. The galaxies we see are, quite literally, the universe's magnified quantum quirks. What's even more remarkable is that without those imperfections, nothing would exist. If the early universe had been perfectly smooth, gravity would have had nothing to work with. There would be no clumps to form stars, no stars to forge elements, no planets, no life. Perfection, ironically, would have meant emptiness. The universe needed those flaws, those tiny ripples, to become interesting. Every imperfection was a seed of creation. This gives a poetic twist to our understanding of existence. The cosmos we know and love, with its galaxies, stars, and living beings, owes its existence to quantum uncertainty. The same randomness that seems so capricious in the microscopic world becomes, on a grand scale, the architect of everything. From the smallest tremors came the largest patterns. From the faintest whispers came the loudest symphony. If you could trace your own atoms back through time, you'd find that their positions were influenced by gravitational wells that began as those very quantum ripples. The calcium in your bones, the carbon in your cells, even the photons that light your eyes right now. All of them owe their place in the universe to a tiny fluctuation in the fabric of space more than 13 billion years ago. And yet, despite the enormity of it all, the process itself is so simple, so inevitable. Space expands, gravity gathers, and structure emerges. It's a reminder that the universe doesn't need external guidance to create beauty. Its own internal laws are enough. Randomness, given enough time and space, can sculpt order. The philosophical weight of that is quietly staggering. Every structure, every planet, every thought you've ever had exists because the universe wasn't perfectly smooth. We are the consequence of imperfection, the embodiment of quantum chance. The universe's fidgeting became galaxies, and those galaxies became us. There's humour in that too, a cosmic irony. The same uncertainty that makes particle physics so unpredictable is what made life possible in the first place. Without the universe's inability to sit perfectly still, there would be nothing to observe, nothing to wonder about. In a sense, the cosmos' greatest creative act was born out of its tiniest fluctuations. The cosmic microwave background, that faint afterglow still shining from the early universe, is a message in light. A whisper from a time when everything we know was compressed into a glowing fog. When we listen closely with our telescopes tuned to its gentle hum, we hear the universe remembering its own beginning. So much of what we call structure, galaxies, clusters, stars, began as noise, but in that noise lay pattern, and in that pattern lay destiny. It's a humbling thought that the grandest creations can grow from the smallest randomness. The next time you look up at the night sky, try to imagine those galaxies as ancient echoes of quantum uncertainty. Each one a ripple made real, a wave frozen in time, a monument to the universe's creative restlessness. Small causes, vast consequences. The universe began as a flicker, and from that flicker, it learned how to shine. If quantum mechanics sounds distant, all about subatomic particles, energy fields, and the birth of stars, it might surprise you to learn that the same strange rules also guide the living world. Life, in its quiet brilliance, hasn't just learned to live with quantum effects, it uses them. Plants, animals, and even the cells in your body take advantage of nature's smallest tricks to make existence possible. It's as though evolution peeked beneath the curtain of classical physics and thought, this could be useful. For much of the 20th century, scientists assumed quantum mechanics belonged only to the microscopic realm, the world of electrons and photons, not birds and trees. Living systems seemed too warm, too noisy, too chaotic to preserve delicate quantum states. After all, quantum effects often collapse when disturbed. Yet, over the last few decades, evidence has shown that life has a knack for coaxing the improbable into reality. One of the most beautiful examples of this is hidden in the quiet efficiency of photosynthesis. Every green leaf, every blade of grass, every patch of algae floating on the ocean's surface relies on an almost miraculous energy transfer process that begins when a photon, a single particle of light, is absorbed by a molecule of chlorophyll. That photon's energy must be delivered with perfect precision to a reaction center where it can be stored as chemical energy. In the classical view, the photon's energy would bounce randomly from molecule to molecule until it found its destination, a slow and inefficient process. But nature has found a better way. Experiments have revealed that during this transfer the energy doesn't choose a single path. It explores all possible paths at once, in a state of quantum coherence. The energy wave ripples through the leaf's molecular structure like a symphony of possibilities, sampling every route simultaneously, then settling on the most efficient one. It's like a traveller trying to find the quickest route through a maze, but instead of wandering around aimlessly, they split into a million versions of themselves, explore every path in parallel, and instantly reunite on the best road. That's quantum mechanics in action, and plants do it effortlessly, every second of every day. This coherence lasts for only trillionths of a second, yet it's enough to boost the efficiency of photosynthesis far beyond what classical physics predicts. It's nature's way of whispering that the quantum world isn't just strange, it's astonishingly practical. But plants aren't the only masters of quantum art. Some birds, particularly migratory species like the European robin, appear to navigate across entire continents using quantum entanglement. For years, scientists wondered how birds could sense Earth's magnetic field with such precision. They don't carry compasses, and the field is far too weak to detect through nerves or muscle. The answer seems to lie in their eyes. Inside the retinas of certain birds, there are molecules called cryptochromes. When struck by light, these molecules form pairs of electrons whose spins become entangled, linked in such a way that what happens to one affects the other instantly, even when separated. The alignment of Earth's magnetic field influences the rate at which these entangled states change, subtly altering the chemical signals the bird's brain receives. In essence, the bird can see the magnetic field not as a colour but as a shifting visual pattern overlaid on its ordinary vision. Imagine flying thousands of kilometres through fog and darkness, guided not by landmarks but by the invisible hum of the planet itself. That's quantum navigation, fragile, improbable, yet exquisitely real. The thought of life using entanglement might sound like science fiction, but experiments in controlled environments have supported the idea. The quantum link in cryptochrome molecules seems to persist long enough to influence biological processes, defying the notion that warm, wet systems can't host such delicacy. The robin, without ever knowing it, has become a natural quantum experiment in flight. And it's not just plants and birds. Even the enzymes that make chemistry run inside your cells rely on quantum effects to do their jobs efficiently. Enzymes are nature's molecular machines, catalysts that speed up chemical reactions, often by factors of millions or billions. They do this by guiding tiny particles like electrons or protons from one molecule to another, but sometimes the barriers between those molecules are too wide for the particles to cross by classical means. So, what does nature do? It tunnels through. Just as in the quantum tunneling that powers the sun's fusion, particles inside enzymes can penetrate energy barriers they shouldn't be able to cross. Instead of climbing over the wall, they simply appear on the other side, making reactions happen far faster than they otherwise would. This process, known as quantum tunneling, underlies everything from how we metabolize food to how our DNA is repaired. Life, it seems, dances effortlessly along the edge of the quantum world. Even processes like smell may have a quantum dimension. Some researchers have suggested that when a scent molecule enters a receptor in your nose, the way it vibrates at the quantum level might help determine how it's recognized. The idea remains debated, but it hints at a recurring theme. Wherever life finds efficiency, quantum mechanics might not be far behind. Of course, it's important to tread carefully here. Quantum biology is a young science, and not everything mysterious about life is quantum. Some popular accounts stretch these ideas into mysticism, claims that consciousness, healing, or telepathy arise from quantum effects. These are poetic notions, but not supported by evidence. The quantum world does underlie everything, but that doesn't mean it explains everything in magical terms. The beauty lies in how real, measurable phenomena, photosynthesis, navigation, enzymatic reactions, harness quantum rules with elegance and precision. It's worth pausing to consider what this means philosophically. Life has evolved within the quantum universe, shaped by its probabilities and uncertainties. It's not separate from them. Every cell is a tiny, physics experiment, finding stability through chaos, structure through chance. The line between physics and biology blurs because, at the deepest level, they are one and the same story. Energy organizing itself into something that can think, move, and dream. The quantum effects we see in living systems aren't signs of mysticism, but of adaptability. Nature doesn't waste good tricks. When something works, evolution finds a way to use it. Whether it's the sun fusing hydrogen through tunneling, or a leaf capturing photons through coherence, the principle is the same. Use the universe's smallest rules to build the biggest wonders. If we could perceive the world at that scale, perhaps life would look less like a collection of separate organisms and more like a vast field of interactions, an orchestra of energy and probability, humming in exquisite harmony. Every photon absorbed, every molecule formed, every heartbeat that follows is part of that same rhythm. The next time you see sunlight filtering through leaves, or a bird tracing invisible lines across the sky, remember that these are not just poetic images. They are acts of physics, life tapping into the quantum engine of the universe. The boundary between the living and the fundamental is thinner than we think. From the trembling of electrons in chlorophyll to the tunneling protons in your cells, life doesn't merely exist in the quantum world, it is of it. Each breath, each moment, is sustained by processes that blur the line between certainty and possibility. Life hums in harmony with the quantum scale, a soft melody that began billions of years ago and still echoes through every leaf, every wing, and every pulse of your heart. If quantum mechanics governs everything, from atoms to galaxies, why doesn't the world around us look quantum? Why don't we see tables in two places at once, or cats that are both asleep and awake? Why do things seem solid, certain, and predictable, when, at their core, everything is built from uncertainty? The answer lies in one of the most subtle and elegant ideas in modern physics, a process called decoherence. Decoherence is the quiet bridge between the quantum and classical worlds, the reason why we can live in a realm of definite shapes and clear outcomes, even though everything underneath is a blur of probabilities. It's not that quantum mechanics stops applying at larger scales. It never stops. Instead, as systems grow bigger, they become entangled with their surroundings in such a way that the delicate quantum behavior we associate with particles, superposition, interference, entanglement, becomes effectively invisible. In the quantum world, a particle can exist in many possible states at once, its wave function describing a cloud of probabilities. But the moment the particle interacts with its environment, with air molecules, light, heat, or even a single photon of stray radiation, those possibilities begin to collapse into one outcome. The quantum wave doesn't vanish in a puff of mystery. It simply spreads its coherence among countless other particles until the pattern is too complex to trace. Think of a single violin playing in a quiet room. You can hear every vibration, every delicate overtone. But if that same violin starts playing in the middle of a thunderstorm, the notes are still there. They're just drowned in the roar of wind and rain. The melody hasn't disappeared. It's been lost in the noise. That's decoherence. Quantum systems are like those fragile notes, clear and distinct when isolated, but quickly overwhelmed by the chaotic orchestra of the environment. In a sense, every measurement we make is just another form of entanglement. When you observe a particle, you're not forcing it to make a choice. You're linking it to a much larger web of interactions. The measuring device, the air around it, the photons bouncing off it, all become part of one enormous interconnected system. The coherence that once defined the particle's quantum state becomes smeared out across so many degrees of freedom that it no longer behaves in a measurable quantum way. What remains is the classical world we recognize. This transition isn't sudden. There's no moment when reality decides to become classical. Instead, it's gradual and inevitable, a continuous exchange between the pure, delicate quantum domain and the noisy, entangled complexity of everything else. The more particles involved, the faster the coherence fades. A single electron can remain quantum for ages, a dust grain for nanoseconds, a cat for even less. To make this less abstract, imagine ripples on a calm pond. Each ripple represents a possible state, overlapping, interfering, creating a beautiful, complex pattern. But then it starts to rain. Each raindrop adds new ripples, new disturbances, until the original pattern disappears into chaos. The pond hasn't stopped being made of water. It's just too disturbed for the original waves to be seen. Likewise, the universe hasn't stopped being quantum. It's just too noisy at large scales for us to see the waves anymore. This constant blurring of quantum states is what allows the world to appear stable. Without decoherence, everything would remain uncertain, smeared across infinite possibilities. But thanks to interactions with the environment, those possibilities are constantly being narrowed down, not through some magical collapse, but through the simple statistical washing out of interference. Macroscopic calm is built from microscopic confusion, and yet for all its serenity, decoherence is not destruction. The quantum information isn't gone, it's just dispersed. In theory, if you could perfectly track every particle in the environment, every photon, every vibration, you could reconstruct the original quantum state. In practice, though, that's impossible. The universe's information web is far too tangled for any observer to unwind. What we call reality is just a practical version of quantum mechanics, the one that emerges when all the fine details are blurred together. This might sound abstract, but it's at the heart of some of today's most exciting technology: quantum computing. Quantum computers rely on maintaining coherence, keeping qubits, the quantum bits of information, in delicate superpositions of states for as long as possible. These superpositions allow quantum computers to explore many possibilities at once, solving certain problems far faster than any classical machine could. But the challenge is monumental. Every stray vibration, every whisper of heat, every cosmic ray that touches a qubit threatens to destroy its coherence. Engineers go to extraordinary lengths to protect quantum systems from decoherence. They cool them to near absolute zero, shield them from electromagnetic noise, and isolate them from the environment with exquisite precision. Even then, maintaining coherence for more than a fraction of a second can be an achievement. The task is like trying to keep a soap bubble intact inside a hurricane, and yet this struggle has taught us something profound. Decoherence isn't a flaw in quantum mechanics. It's the very reason we can experience a stable world. If coherence lasted forever, the boundaries between possibilities would never settle, and now would never arrive. In a sense, decoherence gives us the present. It allows quantum potential to crystallize into classical experience. The more you think about it, the more it feels like the universe is performing an endless act of translation. At the smallest scales, it speaks in probabilities and waves. At the largest, in certainties and forms. Every interaction, every exchange of energy, every observation is part of that translation, a conversation between quantum truth and human perception. We tend to imagine the quantum and classical worlds as separate layers of reality, but they're not. They're the same thing, seen at different levels of resolution. Quantum mechanics is the raw fabric. Classical physics is the tapestry we see when we step back far enough. It's the same universe, just viewed through different lenses. This idea has a quiet beauty to it. The predictability of our world, the solidity of a table, the reliability of gravity, the comfort of cause and effect, all emerge from a foundation that is anything but predictable. Underneath the calm surface of the everyday world lies a sea of fluctuations, constantly jostling, entangling and decohering. The fact that we don't see that chaos directly is what allows us to exist within it. So, the next time you reach out to touch something solid, remember that what feels certain is built from uncertainty. Every object, every atom, every moment of experience is the product of decoherence, the quiet averaging out of quantum strangeness into classical order. It's easy to think of this as a loss, as though the world has been tamed, its wonder hidden beneath the ordinary. But really it's an act of balance. The universe has found a way to let chaos give rise to stability, to let uncertainty give birth to experience. Macroscopic calm is built from microscopic confusion, and in that calm we find the space to live, to think, and to wonder where all the quiet strangeness might still be hiding, just beyond the reach of our everyday senses. Beneath the surface of everything, beneath the atoms, beneath the particles that make those atoms, beneath even the emptiness between them, there lies an invisible architecture. It is not made of matter, nor of energy as we normally imagine it. It is a vast web of fields, stretching everywhere, shaping everything, and humming with constant motion. This is the quiet foundation of the universe, a hidden structure known in physics as the Standard Model. It's our best description of reality at the most fundamental level, and it tells us that everything that exists, from light to electrons to the forces that bind them together, arises from interacting quantum fields. Not tiny particles floating in a void, but continuous fields overlapping in perfect mathematical harmony. Imagine the universe as an immense vibrating ocean. Each type of particle is not a separate object, but a ripple, a localized excitation on one of these underlying fields. The electron field ripples to create electrons, the photon field ripples to create light, the quark fields ripple to create the building blocks of protons and neutrons. Everywhere, all the time, these fields coexist, interacting, resonating, and occasionally flaring into existence as what we perceive as matter. It's an elegant picture, one that replaces the old idea of particles as little billiard balls with something infinitely smoother and more beautiful. There are no edges in this reality, only waves overlapping waves, endlessly exchanging energy. Matter in this view is simply a standing pattern, a note in the grand cosmic symphony of fields. These fields don't just coexist, they're interwoven through deep symmetries called gauge symmetries. In everyday language, a symmetry means something that stays the same when you change how you look at it, like a snowflake remaining perfect no matter how you rotate it. In physics, symmetries are even more powerful. They are nature's rules for how forces and particles remain consistent as they interact. Gauge symmetries are the invisible threads that hold the fields together, ensuring that as they vibrate, they do so in harmony. Every force of nature, electromagnetism, the weak nuclear force, and the strong nuclear force, arises from these symmetries. They are like the grammar of reality's language, defining how energy and matter can communicate. When you see light, you're witnessing the electromagnetic field speaking through its symmetry. When an atom's nucleus holds together against the incredible repulsion of its protons, it's the strong forces field doing the talking. The beauty of this structure is its consistency. Despite the variety of particles and forces, everything obeys the same core principles. Different fields are simply different expressions of the same deeper symmetry, like different instruments playing from the same sheet of music. And then there's the Higgs field, the quiet, ever-present undercurrent that gives the entire system weight and substance. Before its discovery, scientists puzzled over why some particles have mass, while others, like photons, glide weightlessly through space. The answer lay in the Higgs field, a kind of universal molasses that fills all of space. As particles move through this field, they interact with it, and in doing so they gain inertia. Some, like the top quark, couple strongly with the Higgs and become heavy. Others, like the electron, barely interact and stay light. The photon doesn't interact at all, which is why light has no mass and can race through the universe at its ultimate speed limit. In 2012, when the Higgs boson was finally detected at CERN's Large Hadron Collider, it was a quiet triumph for this entire vision of reality. The discovery didn't just confirm the existence of one more particle, it confirmed the structure of the fields themselves. It proved that the Standard Model's web was not just mathematical poetry, but a true description of how the universe is built. What's remarkable is how serene this architecture is, despite its complexity. Each field dances in harmony with the others, their interactions governed by simple yet profound equations. The electromagnetic field blends seamlessly into the weak force at high energies, unifying into a single electro-weak field. Physicists suspect that at even higher energies, such as those that existed just after the Big Bang, all forces might have been unified. One grand field humming with perfect symmetry, later breaking apart as the universe cooled. That breaking of symmetry, the cosmic cooling that fractured unity into diversity, may be the reason we have structure at all. When the universe was young and uniform, everything was balanced. As it expanded and cooled, symmetries broke, and fields settled into new configurations. That process gave birth to the distinctions we know: matter and radiation, forces and particles, attraction and repulsion. The variety of the cosmos from starlight to stone is a direct consequence of broken symmetry. It's humbling to realize that every particle in your body is a ripple in this unseen sea. The electrons orbiting the atoms in your cells are tiny disturbances in the electron field. The protons and neutrons in your nucleus are knots in the quark and gluon fields, held together by the strong interaction's elegant geometry. Even the gravity that binds you to the Earth, though not yet fully understood in quantum terms, may one day fit into this same framework, another note in the symphony of fields. The universe is not a collection of things, it's a pattern of relationships, a self-sustaining network of vibrations that never stops moving, even in apparent stillness. When you look around and see solidity, you're really seeing stable patterns in this ocean, like standing waves that persist in time. There's a quiet beauty in how the Standard Model, despite its intimidating name, feels less like machinery and more like art. It doesn't describe a cold, clockwork cosmos, but a living fabric, woven from energy, structured by symmetry and sustained by balance. Every particle, every interaction, Every glimmer of light follows from that design. And yet, for all its precision, the standard model is not the final word. It leaves mysteries untouched. Dark matter, dark energy, gravity's quantum nature. It's as though we've traced one exquisite section of the cosmic tapestry, but the edges still disappear into shadow. Perhaps deeper symmetries await discovery, hidden in dimensions we cannot yet perceive. Perhaps the universe, like any great work of art, will always retain a hint of mystery, just enough to keep us looking closer. For now, it's enough to appreciate what we do see. The unity beneath the chaos, the music beneath the noise. The fields hum softly beneath all things, invisible yet ever present, keeping balance, trading energy, giving rise to everything from the smallest particle to the brightest galaxy. The hidden architecture of fields is not just a theory of physics, it's a testament to the elegance of nature's design. The deeper we look, the less the universe resembles machinery, and the more it resembles harmony. A woven fabric of vibration and balance, serene, eternal, and astonishingly beautiful. Before there were stars, before there was light, before even space and time had meaning, there may have been only a tremor, a whisper in the quantum fabric of nothingness. It is one of the most profound questions that science has ever dared to ask. If energy cannot be created or destroyed, then how did everything begin? How did the entire universe emerge from what seems to be absolute emptiness? To begin imagining that, we have to let go of the everyday meaning of nothing. In the language of quantum physics, nothingness is not a flat, silent void. It's more like a restless sea, filled with invisible energy and fleeting fluctuations. Even in perfect vacuum, the quantum fields never truly sleep. They quiver, shift, and exchange energy for the briefest instants of time, creating pairs of particles that appear and vanish again before the universe even notices. This restless state is called quantum vacuum fluctuation, and it may hold the secret to how something came from nothing. At unimaginably small scales, such fluctuations are constant, a cosmic jitter that never entirely settles. And if the early universe was once small enough, far smaller than a proton, far denser than any star, then those fluctuations would not have been side effects. They would have been the main event. It's possible that the Big Bang itself was triggered not by an external cause, but by a quantum fluctuation in the primordial vacuum magnified into existence by its own energy. In this view, creation wasn't a moment when something violated the laws of physics. It was a moment when the laws themselves allowed a spontaneous transition, a shift from potential to reality. Quantum theory permits such transitions, so long as the total balance of energy remains zero. If that sounds paradoxical, imagine a simple scale. On one side sits positive energy, matter, radiation, motion. On the other side sits negative energy, the gravitational pull that binds everything together. When you add them up, the universe may, astonishingly, equal nothing at all. That is the essence of the free universe hypothesis, that the cosmos could arise spontaneously without violating conservation laws, because the sum total of its energy is perfectly balanced. The expansion of space creates gravitational energy that offsets the energy stored in matter and light. It's like an intricate accounting trick at the heart of creation. Everything from nothing, yet nothing lost. During the universe's earliest moments, this delicate balance may have been supercharged by an event called cosmic inflation. Inflation is the idea that, in the first fraction of a second after the Big Bang, the universe expanded exponentially, faster than light, faster than thought, stretching quantum ripples into vast structures. The energy driving that expansion likely came from the vacuum itself, a form of stored energy associated with a field that permeated all space. When that vacuum energy released, when the inflation field decayed, it unleashed an immense flood of particles, radiation, and structure. The universe heated, glowed, and began to evolve into the cosmos we now observe. Every star, every atom, every heartbeat that would ever exist began as a flicker in that burst of expansion. Inflation didn't just make the universe large, it also made it smooth. Quantum fluctuations, amplified to cosmic scale, became the seeds of galaxies. The same tiny jitters that once defined the behavior of particles now define the distribution of stars across billions of light years. The fingerprints of those first quantum ripples are still visible today in the cosmic microwave background, the faint afterglow of creation that fills the night sky. It's humbling to realize that the grand structures of the universe, clusters of galaxies, webs of matter, the very existence of cosmic order, were sculpted by randomness. The largest patterns we can see owe their existence to the smallest uncertainties imaginable. When we think of the Big Bang, it's easy to imagine an explosion happening somewhere in pre-existing space. But that image is misleading. The Big Bang didn't happen in space, it created space. Before it, there was no where or when. Time itself unfurled along with the universe. Asking what came before the Big Bang is like asking what's north of the North Pole. The question loses meaning because the coordinate system itself ends. And yet, quantum mechanics allows us to explore even this conceptual edge. Some cosmologists propose that our universe could have emerged from a prior quantum state, a timeless, probabilistic foam where universes constantly flicker into and out of being. Most of them vanish almost instantly, their expansion collapsing before it begins. But once in a while, a fluctuation crosses a threshold and inflates, creating a full-fledged cosmos, self-contained, self-sustaining, and complete. It's possible, then, that our universe is just one bubble in a vast eternal sea of quantum creation. Each bubble would have its own laws of physics, its own constants, its own story. Most would fade quickly. A few, like ours, might grow old enough to give rise to galaxies, planets, and the strange phenomenon of beings who can ask where they came from. If this is true, then the Big Bang wasn't the beginning of everything, but the beginning of our patch of everything. One verse in a cosmic symphony that has no final note. This perspective leads to a quietly astonishing realization. Existence itself may not require an external cause. The universe might simply be what happens when potential meets probability. The laws of physics, or perhaps the deeper rules that give rise to those laws, may make existence inevitable, like a song that must be sung once the instrument is tuned. And yet, for all its elegance, this idea is not about cold equations, it's about balance, the kind of perfect symmetry that feels almost poetic. The total energy of the universe might indeed sum to zero, yet that zero is filled with meaning. The positive energy of matter and light is matched by the negative energy of gravity, leaving a net result that is, astonishingly, nothing. But it is a nothing that glows, expands, and dreams. This concept isn't just theoretical musing, it's supported by observations. The universe appears to be remarkably flat, meaning its geometry perfectly balances energy and gravity. The cosmic microwave background reveals no edge, no preferred direction, no sign of external influence. Everything we see fits a universe that created itself from its own quantum potential. expanding into the balanced, self-contained cosmos we inhabit today. It's almost as if existence is a perfect equation written across the void, where every positive term is mirrored by a negative one, and the total remains unchanged. When you think about it this way, the mystery of creation transforms from "why is there something instead of nothing" into "how could there not be?" If quantum fields can never rest, if even the deepest vacuum still hums with energy, then perhaps the emergence of a universe is not an anomaly but an inevitability, the natural expression of a restless reality that refuses to stay empty. And yet, even that answer leaves us with awe, because if existence is the ultimate symmetry, then everything we know, every atom, every thought, every heartbeat, is part of that perfect balance. The cosmos may have emerged from nothing, but it did so in a way that conserved everything. No energy was stolen from beyond, no law was broken, no miracle was required. Perhaps existence itself is the miracle, the equilibrium of opposites so profound that it gives rise to stars, to consciousness, to the quiet beauty of wondering why. When physicists contemplate this balance, they often describe it as a kind of cosmic accounting. Positive energy in one column, negative energy in another column another, all perfectly reconciled. But maybe it's more than accounting. Maybe it's the language of creation itself. Perhaps existence is the ultimate symmetry. Everything from nothing, perfectly accounted. After wandering through the strange and shimmering world of quantum energy, it's easy to feel as though you've stepped out of a dream. Everything we thought was solid has dissolved into vibrations and fields. Everything certain has turned to probability. And yet, what emerges from that strangeness is not confusion, but harmony. The deeper we look into the quantum world, the more we find coherence beneath the chaos, a quiet order pulsing through the smallest scales of reality, linking every atom, every photon, and every star. Quantum energy began its story humbly, with Max Planck trying to fix a simple problem about how things glow when heated. He wanted mathematics to behave. Instead, he uncovered a new truth about the universe. Energy doesn't flow continuously like water. It comes in packets, tiny quanta, discrete steps in nature's otherwise seamless dance. It was as if the universe, when playing its music, could only strike specific notes, never slide between them. That single idea, that energy comes in quanta, was the seed from which all of modern physics grew. Einstein turned that seed into light itself, showing that photons were not just waves but particles, each one a quantum of energy. Bohr used it to explain how electrons circle the nucleus like musicians hitting exact harmonics, never playing out of tune. Schrödinger turned it into a song of probabilities, where particles became waves and waves became possibility. And Heisenberg revealed that certainty itself was an illusion, that the more precisely we try to measure one thing, the less we can know about another. This uncertainty isn't a flaw in the design, it is the design. It's what allows the universe to exist in motion rather than stillness. Without it, particles would freeze into perfect silent order, and no change, no life could ever occur. Reality's restlessness is not chaos but creativity. At the foundation of all this is the concept of fields, invisible sheets of energy that fill all of space. Everything we see, from light to matter to heat, is a ripple in one of these fields. You're made of ripples in the electron field, held together by ripples in the gluon field, warmed by ripples in the photon field. Space isn't an empty container, It's a living ocean of interaction, and within that ocean, energy never disappears, it only changes form. That's the law of conservation, one of the simplest and most profound truths in science. No matter what happens, a star collapsing, a leaf growing, a thought forming in the human brain, the total energy of the universe remains constant. It can stretch, shift, radiate, or transform, but never be lost. Even when matter seems to vanish, as in the annihilation of particles, its energy reappears in another form. The universe keeps perfect books. In this light, existence begins to look like a great circulation, a ceaseless exchange between forms of energy. The photons streaming from distant galaxies were once locked inside atoms forged in stars. Those atoms were built from energy released in the early universe. That energy in turn emerged from quantum fluctuations in the void, and some of it, after billions of years of cosmic recycling, now powers the cells in your body. You are, quite literally, made of ancient light. Energy slowed, organized, and condensed into thought. It's a humbling idea, and a funny one too. You're powered by the same cosmic jitters that light the stars. The warmth in your skin and the glow of the sun both come from the same fundamental quanta, excited in different ways. Every breath, every heartbeat, every spark of awareness is just energy changing its costume, moving from one form of existence to another. Quantum physics shows that beneath every calm surface lies motion, jittering, flickering, vibrating. The vacuum isn't truly empty. At every point in space, quantum fields are alive with zero-point energy, constantly shifting between potential and presence. Even nothing is busy. And it is from this restlessness that order arises. On the cosmic scale, that same quantum hum may be what inflated the universe at its birth, stretching space and time themselves. Tiny fluctuations magnified by cosmic expansion became galaxies, stars, and the atoms in your body. The infinite quiet of the early vacuum became the chorus of existence. From nothing came everything, not through miracle, but through balance. Positive and negative energy, matter and gravity, perfectly countered so that the sum remains zero. It's a breathtaking symmetry. Every motion in the universe is part of this balancing act. The light of stars is balanced by the pull of gravity. The expansion of the cosmos is offset by its invisible curvature. On every scale, energy flows like a tide. Never gained, never lost, always transformed. The result is a reality that sustains itself, powered by its own harmony. The more we study quantum energy, the clearer it becomes that we live not in a world made of things, but in a world made of relationships. Fields interacting with fields, waves overlapping, probabilities blending. The solidity of a table, the sharpness of light, the persistence of memory, all are manifestations of patterns, not particles. Matter is what happens when energy dances in formation, and what a dance it is. From the smallest particle to the largest galaxy, the universe moves in rhythm with itself. Electrons leap between energy levels, emitting photons that race through space, strike another atom, and set off the next event. Stars fuse hydrogen into helium, releasing light that travels for billions of years to fall upon a planet that uses that same light to grow forests and fuel life. Even thought, that flicker of consciousness, is electrical energy rearranging itself in the quantum web of your neurons. The entire cosmos is one vast network of exchange. There is no stillness anywhere, not truly. Even at absolute zero, the lowest possible temperature, quantum energy continues to hum softly beneath the silence. Reality never sleeps. Perhaps that's why we find such peace in contemplating it. The universe's order doesn't arise from control, but from constant movement. It's a kind of balance that includes uncertainty, a stability born of impermanence. We don't need to understand every equation to feel the wonder of that. It's enough to know that even the quietest moment, even the stillest night, is alive with hidden motion. When you think of quantum energy not as an abstract theory, but as the pulse of everything, it becomes something deeply personal. The energy in your body once shone in stars. The carbon in your cells was forged in stellar cores. The light that lets you see these words began its journey millions of years ago, and when it fades, its energy will still exist, transformed, never lost. That's the most astonishing truth of all. Energy connects everything that ever was or will be. It's the thread that ties together atoms, stars, galaxies, and life itself. It has no beginning and no end, only transformations. Every sunrise is recycled starlight. Every heartbeat echoes ancient fusion. Every flicker of thought is powered by the same energy that first rippled through the void before time began. Science, for all its precision, has a quiet poetry. When we trace energy from its quantum origins to our own existence, we're not just learning about physics, we're glimpsing the unity of reality itself. The boundary between you and the universe dissolves, and you begin to see that they are not separate. You are a pattern woven from the same fields that fill all of space. It's tempting to wonder whether the universe knows it's alive, or perhaps it doesn't need to. Through us, it already dreams, observes, and contemplates itself. Each act of thought, each moment of awareness, is energy reflecting upon energy. The cosmos turning inward to see what it has become. And that brings us back to where we began, to the question of what quantum energy means. It means that the universe is not static or mechanical, but creative and continuous. It means that everything we see, from the flicker of an atom to the fire of a star, is part of the same story of transformation. It means that even the smallest tremor in the vacuum can blossom into a galaxy, and that no energy, once born, ever truly dies. Energy is the universe dreaming itself alive, endlessly transforming, endlessly returning, endlessly awake. From a single spark of curiosity in the mind of Max Planck to the boundless hum of the cosmos itself, our journey through quantum energy has traced the universe's most delicate heartbeat. What began as a question about how light glows from a hot surface has led us to a truth so vast it nearly slips beyond comprehension, that everything, from the smallest atom to the grandest galaxy, moves to the same invisible rhythm. The world you know, solid, bright, reliable, rests atop this sea of restless motion. Every breath of air, every photon of sunlight, every pulse in your wrist is part of an unbroken chain that began before time itself. Energy flows through all things, quantized yet continuous, discrete yet eternal. It changes shape endlessly, never vanishing, always finding a new form to inhabit. There is a quiet grace in that constancy. Beneath every transformation, the birth of stars, the flicker of light, the simple act of thought, lies the same conserved quantity, the same pulse of existence that first stirred when the universe awoke. Energy is not something the cosmos has. It is what the cosmos is. Think back to where it all began, to Planck's discovery that energy comes in tiny packets, like coins minted in the furnace of reality. That small idea shattered the illusion of smoothness and revealed the pixelated texture of existence. Then came Einstein, turning light itself into a stream of quanta, photons carrying the currency of the universe across space. Bohr followed, showing that atoms are not miniature solar systems but musical instruments, their electrons leaping between harmonics. Schrödinger gave the world a new image, matter as melody, probability as poetry. And Heisenberg reminded us that perfection of knowledge is not possible, because uncertainty is woven into the fabric of creation. From those ideas, everything else unfolded. The realization that particles are ripples in fields, that vacuum is never truly empty, that even silence carries a hum. This same mathematics that describes the dance of electrons in an atom also explains the first tremors that gave rise to galaxies. Every point in space, every mote of dust, every flicker of light carries the same essential law. Energy moves in quanta, and those quanta obey the music of probability. It's easy to get lost in the abstractions of quantum theory, wave functions, fields, superpositions and symmetries. But at its heart, it's not about complexity, it's about connection. The same rules that shape the behavior of photons in a laboratory also govern the glow of a distant star. The same quantum tunneling that lets particles escape atomic barriers also powers the fusion that keeps the sun alive. The world is not divided between the large and the small, the near and the far. It's all one continuous conversation of energy. Even the emptiness between stars is alive with potential. Space is not void but vibrant, trembling with zero-point energy, pregnant with possibility. Out of this trembling came the universe itself, born not from something, but from balance, from perfect symmetry between the positive and the negative, the visible and the unseen. The cosmos does not need a spark from beyond to begin. It carries its own ignition within. And yet, for all its motion, there is a strange serenity to the universe. The fields hum, but they hum in harmony. Forces balance, probabilities smooth into patterns, and from the chaos of quantum noise, order emerges. Galaxies spiral in quiet perfection. Stars burn for billions of years with steady light. Life arises from the interplay of randomness and rule, and eventually that life looks back at the sky and wonders how it all began. You're part of that reflection. You are the universe observing its own energy through the lens of consciousness. Every thought, every heartbeat, every dream is another expression of quantum energy, organized, momentary, and infinitely precious. You're not outside the physics that governs the cosmos. You're that physics, slowed and softened into life. It's comforting to realize that in a universe ruled by uncertainty, conservation offers a quiet promise. Nothing is ever truly lost. The energy that fuels your body was once starlight. The atoms that build you were once plasma drifting in the newborn cosmos. When your energy returns to the world, it will take new forms, perhaps as heat, as light, as growth in something else. In the great exchange of existence, nothing is wasted, and nothing truly ends. Perhaps that's what makes quantum energy so calming to contemplate. It doesn't suggest chaos or randomness, but rather an endless continuity. Even when things dissolve, they persist in new patterns. Even when silence falls, motion continues underneath. The universe never truly stops moving. It only softens its voice. That quiet is everywhere, if you listen, in the gentle pull of gravity holding you to earth, in the shimmer of sunlight on water, in the slow rotation of galaxies billions of light years away. Energy flows through all of it, connecting past and present, matter and thought, dust and flame. To understand quantum energy is to see that the universe is not built from separate pieces, but from a single, unbroken whole. A symphony of quanta playing endlessly in variation. Sometimes the notes are loud and bright, the explosion of a supernova, the spark of lightning. Sometimes they're soft, the drift of a cloud, the rhythm of a heartbeat. But the music never stops. It simply changes tempo, changes key, changes form. And now, as our journey draws to its quiet end, there is no grand finale waiting. Just the same calm hum that began it all. The background tone of existence, still vibrating, still alive. From Planck's first spark to the cosmic whisper of empty space, everything follows the same law. Energy flows, transforms and endures. You don't need to hold every detail of the science in your mind to feel its truth. You can simply let the idea settle, like light filtering through water. You can rest in the knowledge that beneath the stillness of your room, beneath the stillness of your thoughts, the entire universe is gently moving, keeping balance. The same invisible energy that lights the stars hums softly within you. The same quantum fields that shaped galaxies ripple through your being. You are part of the pattern, a fleeting yet eternal arrangement of the universe's own energy, experiencing itself for a little while as human. And as you drift towards sleep, you might take comfort in this, that the cosmos, vast and unending, is at peace with its motion. Its energy hums quietly, changing shape but never ceasing. The night around you is not empty. It's alive, full of gentle vibrations too small to see, too quiet to hear. The universe never truly stops moving. It only softens its voice. And now, in that softening, you can let the silence complete the thought.